So welcome. Tonight is actually the 2021 Fall International Astronomy Day. For those that celebrate it.
We're
Yes.
celebrating looking at clouds.
Yes, I was just going to say, and as I said in the email, when I was writing the email this afternoon, it was pouring down rain, and I read the weather forecast, which included thunderstorms and hail. And I went, I guess we're not looking up tonight. The rain has stopped, but the cloud cover's still there, so nothing to see, as the saying goes.
When it stopped, it
And
made a
that was
beautiful.
very nice conjunction of Venus and the moon, and they would be about the same phase. So that would be awesome if we could look at the telescopes, like have public to look at the telescopes.
Well, they're going to try to do that at Markham Park next week.
Oh, okay. Do you know if they're going to be using their new camera?
I think so.
Okay.
So, but they have a problem. They can't line up on Polaris because of the Australian pines.
Well,
So
they'll just request the park management to cut them all down.
yeah, and they said they'll do their best.
Yeah.
So,
Well, if you went with an altitude azimuth mount, like I know a couple of the members own, like, you know, Les and Steve actually own Ioptron altazimuth mounts. You don't need Polaris for those.
okay.
Now, when you're showing a live image, also you don't worry about the rotation of the field. But if you're going to stack it for more than 3 minutes at a time, then you got to worry about rotation.
Makes
So,
sense. Yeah.
Anywho, there are 2 International Astronomy Days per year. There's a spring one, usually in the March-April timeframe. And then there's the fall one, which is usually sometime in October. There's actually an International Astronomy Week, and they make International Astronomy Day the Saturday of that week. They'll typically look for some kind of lunar positioning so that people have something to look at. But next Saturday is the 2021 International Observe the Moon Night. And I don't know why they picked, I don't know why, yeah. I don't know why they picked next week, because at least for South Florida, the moon will be better this week than next week. But, you know, they do what they do. So on with the news. In the never-ending saga of Boeing and their lack of success with the United Launch Alliance program, NASA really stuck it to them this week. They took 2 of the astronauts that had been assigned to the Starliner program, and they transferred them over to the SpaceX Crew Dragon program. And that was shortly after the United Launch Alliance said, you know, we're not going to be able to launch anything with people in it until sometime late next year. And we're not going to be able to launch even unmanned things like our next step in the process to get it to the ISS until, oh, I don't know, maybe mid to late first quarter next year. And so NASA said, we got to get these people up to the ISS. They're on a schedule. So they asked SpaceX, do you think you could do it? And SpaceX not only said, yes, we can. They're actually building 2 more Crew Dragon spacecraft because they're looking for more business from NASA. If you remember the competition between United Launch Alliance, aka Boeing, and SpaceX, they threw billions of dollars more to Boeing than they did SpaceX, by about $2 billion difference. And ULA has yet to successfully launch something to dock with the International Space Station. And SpaceX has already docked I think it's 2 uncrewed and 2 crewed capsules to the International Space Station. They're going to launch another one on the 30th of this month, and then another one, the new one, in April of next year. So they're forging ahead, as the saying goes. And just to keep your space program straight without a program, there's also the Space Launch System, the NASA SLS, and they've had some setback as well. And they're not going to be launching there as yet to make it to the International Space Station trial launch until April of next year. And they're blaming it on COVID and Hurricane Ida. Okay, COVID might take a little longer. Hurricane Ida, where are they launching this thing from? You can't launch it from Houston. And it would be a typhoon if it was on the West Coast. And Ida didn't hit the Cape in Florida. So they're sort of grabbing straws to say, it's not our fault. We really are on track. Yeah, well, you're off track and you're not launching. But that contract can't go away because that launch system is paid for by your tax dollars. It's not a commercial side project. So we'll see where that goes. In an effort to make it easier to send landers and rovers to Mars, they're requesting that the bioprotection regulatory effort be dropped. This is the thing that says, thou shalt thoroughly sterilize thy spacecraft before sending it to Mars, because we don't want to contaminate Mars with human germs, with stuff that already exists on Earth. And I see this as kind of a fake maneuver, because if you remove the protection that says sterilize it before it gets to Mars, and all of a sudden the spacecraft finds something on Mars, well, they can just claim that, well, that came from Earth. See, there's nothing on Mars, that came from Earth. And they've actually done this twice, once with Curiosity and once with one of the Viking missions where they detected organic indications, complex biologic indications, not cells, but let's just say the starter products or byproducts of them. And then they said, no, those probably came from Earth. But by dropping this requirement to sterilize thy spacecraft, they can claim anything they find, it came from Earth, until they find something fossilized that's been around there for, I don't know, millions of years. That obviously didn't come from Earth unless it's reverse panspermia. Something hit the Earth, blew off a rock that had bacteria and viruses on it that then impacted on Mars. And see, that's how Mars got life. It never had any of its own.
It's more likely to be the opposite because Mars has less gravity. So if something blow out of Mars,
that's why I referred to it as reverse panspermia, because it's far more likely that life on Earth began as something that came from Mars than the other way around. But they need to make sure it's old stuff that they find in fossils, not, maybe 50 years old, but certainly hundreds, if not thousands or millions of years old, because we've been sending things that impact the Mars atmosphere and land on Mars since the 1960s. So they did some more analysis of the data they already had from Perseverance regarding the Jezero crater, and they found out a couple of things. One is, yes, there is stratified rock along the outer perimeter of Jezero crater, which means that there was a lot of water there, and it drained away over a very long period of time so that the rock would be stratified. But what they didn't expect to find was out on the plains of Jezero crater, they found giant boulders. How did the boulders get there? They're not associated with any nearby rock formations, and they're too far away to have sort of rolled downhill. It had to be that large flows of water pushed the boulders.
Glaciers.
Possibly glaciers as well, but they have to be big because these are boulders that are like 20 feet across and weigh tons.
If it's very big, it's most likely glacier than a river.
And if it's glaciers, it means that the water froze and stayed there for likely tens of thousands to hundreds of thousands of years, which gives it even more opportunity for life to have come about in the water, in the ice. But the funny thing that NASA responded to that by saying, we'd like to go over there and look at the stratified stuff, maybe, you know, pick away at it and see if we can find anything. But it's just too far away. It's inside the crater. The crater's a couple of 100 miles across, and you knew where you were going to land. And it is a rover, isn't it? Oh, but it's too far away. Okay, we'll, you know, stop asking the questions. You know, it's like me when I ask the question, can't you take that robot arm that you have and maybe, you know, lift up a rock and see what's underneath it? Maybe there's some moss under there. Who knows? But no, they're not equipped to do that. How about the next rover you send? Has a little stronger arm where you can lift up a light, you know, couple of pound rock. And in another one of those climate change things, you remember me a couple of weeks ago mentioning that there's a couple of giant lakes in the western part of the U.S., Lake Mead and Lake Powell. They were down a bit. And back then they were only down, about 70 feet. They're now down 150 feet due to the water drying up and not coming back in the form of rain. So they're now seeing that rock formations that have been underwater for hundreds of years are now being exposed, and they're snow white because they haven't seen light in a long time and they're basically bleached by the sunlight. They also have a problem that ships that were in the lake that were submerged, how do you get rid of your junk ships? You just sink them. Those sunken ships are now starting to show up as sticking up from the water level because the water level is so low. So those are indications, but the one that's really bad news is they've got parts of these lakes that are now mud flats, which means they're at the bottom of that part of the lake. When the water level is that low, you're not going to be drawing drinking water from it, and you certainly don't have enough water volume to run the power generation turbines because you don't want all that bottom silt into the turbines because it will heat them up and cause them to lock up. So I think they need water and electricity now, but I don't see any major efforts to fund anything to solve this immediate problem. So stick a shallow push pin in it. We'll probably get back to that in the next few weeks to months. And yes, William Shatner, Captain Kirk, will be flying on the next Blue Origin launch, which is due on October 12th. I guess that's next week. But my concern is he's 90 plus. He's not in good physical condition. I mean, he's great for a guy 90 years old. But when you see pictures of him, he's a little inflated.
Plump.
He's a little plump, yes. And I think that it's probably kidney issues because his body is retaining so much water, which says he probably is a bit plump and obese, and expecting him to climb 5 flights of metal stairs to get from ground level to the capsule. I don't know if they've thought about that.
They don't have an elevator?
No. Bezos didn't spring for one. And if you watched Wally Funk, who was 82, she was the previous oldest person to go into space. She was in good shape, but she was breathing heavy when she got to the top and just sort of stood around and didn't talk to anybody for a few minutes until she regained her breathing. I can see Shatner making it up maybe 3 flights at most, and then having to call it a day.
Well, didn't they test him out before this to go up and down the stairs?
You would think so. And they asked Wally Funk about that. How many times did you have to climb the stairs? Twice. Once to see if she could do it, and the second time was the day of the launch. And they don't put them through.
Wow.
They don't put them through a physical exercise program. It's literally about a couple of days worth of training, and that's it before you fly on Blue Origin, because Blue Origin is fully autonomous. There is no pilot or co-pilot. There's just a commander who's the guy in charge in case something goes wrong. So the presumption is if you fly on Blue Origin, you can be any member of the public. So they're putting this to the test with the 90-year-old, a bit plump Shatner.
That's the proof of concept.
Yeah. But, something in the back of my mind says they found somebody older and now Wally doesn't have the record anymore. That just stinks. They didn't
How
even
old was
let her
John
retain
Glenn?
They didn't
John
even-
Glenn went up.
It
They
makes
didn't
me,
even, no, Glenn was 78, I think it was. Wally is 82.
it
So,
makes me,
so Wally Funk is currently the oldest person to ever go into space. Now it's a suborbital, so she just went up and then down, no orbiting. The SpaceX commercial crew that recently flew, they had to go through 6 weeks of genuine astronaut training, including physical exercise. So they had to be in peak physical condition before SpaceX would let them fly on the capsule.
it makes me smile though that Shatner is going up there. And then that woman will still be able to claim being the oldest woman to go.
Yes, she will be she's still the oldest woman to do it. But couldn't they have at least given her, 6 months or a year or something holding the record before they brought Shatner on? No. Bezos wants his Blue Origin PR campaign against SpaceX.
Especially because he kind of put his foot in his mouth when he was saying thank you to his employees and stuff, like if it wasn't for you, I wasn't here.
Mhm.
But it sounds like you're my slaves and you work everything and now look at me kind of thing. And everybody, was pissed with him. So maybe he's using Shatner just to look a little bit better.
And if he's using Shatner to look a little bit better, which I think you're right, then also he would be looking at the fact that he wants Shatner to be in as best, he doesn't want Shatner to go up there and die or come back to Earth and die. So he's got to be,
I don't think he's,
going to help him with his, with his company.
I think that if Shatner made it into the capsule, he would be fine. My concern is he may not make it to the capsule. He won't die, but he'll become so exhausted that there would be concern for him to have a cardiac event.
Well, then he wouldn't go. That would be very sad.
Right. That would be sad for Blue Origin, but even more sad for Shatner.
Exactly, very sad. It'd be sad for publicity too. It'd be sad for the whole event because I would be sad if he doesn't get to go.
But wait a minute, what better place would there be for Shatner to go than outer space? Or
Exactly.
space.
And so he's got to get into space first.
Yeah.
There are science fiction actors that are more involved in space exploration. That would
Like
be
Nichelle
better.
Nichols.
No, she's very ill. She wouldn't physically make it up the first flight of stairs.
I mean, she's more involved because if it wasn't her, a lot of half of the women that became astronauts became because of her, because she did campaigns, she visited universities, she worked for NASA and she flew on Sophia.
But who is it that's actually an amateur astronomer that's actually a part of the Star Trek family?
I do
Tuvok.
not know. Huh?
Tuvok,
Tuvok.
the
Oh,
Vulcan
okay.
from Voyager. Yes, he's done many promotional programs for NASA.
Oh, okay. I didn't know that.
Yeah.
I haven't seen
And
any.
he's in reasonable shape and he's younger. I think he would have been excellent. And he would have gotten a lot of the younger audience for Blue Origin, which they could sorely need.
So you don't think that Shatner will attract the younger audience?
No,
Nobody even knows who he
No.
is.
no.
When I was teaching high school, when I mentioned stuff from Star Trek, they go like, hmm? They
Yeah.
had no idea.
Well, he can go up on the Enterprise shuttle, right? It doesn't have any engines or heat shield.
I don't think they fly that anymore. In fact, the
They
actual
never did
Enterprise,
fly. It
the
never-
actual Enterprise space shuttle never made it into space. They
Right.
just flew piggybacked on the back of a 747.
That's right.
They picked the wrong shuttle to name that. Enterprise.
Bad. I didn't realize it never made it into space.
No.
Oh, yeah, there was
The
a
one
big,
they named Enterprise was great for a PR stunt, and they had the whole crew out there, and but
Everybody got pissed because it was the fake.
it didn't even have any engines in it. It just had a tail cone covering where the engines go.
Oh, no.
Yeah, it was basically an aerodynamic prototype to see if they could fly the shuttle on the back of the 747.
So that worked though, right?
Yes,
So it did show what they wanted to know,
yes, it was a proof of concept that did work.
but it sure did fool a lot of people because we thought it would be different. We thought it was going to outer space.
I tell you, the hype over information is such that if you take it at face value, you probably are getting it wrong. You have to do your own delving into things, because even the people that are hyping it know better, but they won't do anything about it because that spoils the charm. How many
Yeah.
times have you seen, oh, this is going to be the best comet in your lifetime, and it's going to be so bright you can see it in the daytime, and it turns out to be like a magnitude 9 by the time it gets close enough to Earth to be seen, which is, you're going to need a good telescope to see that on a dark sky. But when they first hype it, oh, it's just amazing. But the guys that are hyping it know better than that. They've done this many times. So
So what do you
Whenever
think
you-
the hype going to be for Shatner? I mean, you think it's going to be a dud when he goes? I don't think
no.
so.
I think
World
he's going.
does know it.
I think
Maybe
he's going to become
so.
totally exhausted about the third flight of stairs on his way up to the capsule.
And I agree
and
with you.
They're just going to say, oh, he's got a health risk, and we've decided he won't fly at this time.
If they were thinking ahead, they'd probably schedule him to have a seat at the third.
No.
Yes,
No,
and then
no.
say it's not a health risk. He can go. He's just scheduled to take a break there.
I think he advertises CPAC machines on TV.
Yeah.
Yes, he does. He advertises not CPAP machines, but cleaners for CPAP machines.
Yeah.
So he has one. I think the real issue here is if Jeff Bezos really wanted to do this right, he'd spend maybe a couple $100,000 and put in a damned elevator.
Yeah.
It's only 5 stories.
Yeah.
It could be a hydraulic elevator or a pulley elevator. Doesn't matter. Doesn't have to, it's not lifting any hefty equipment. It's just lifting, maybe 2,000 pounds worth of people.
So if you found that he did install an elevator there, then you would be happy.
If he did install an elevator there, I think Shatner could make the trip, and I think it would be good PR value for both Shatner and Blue Origin. But in the absence of an elevator, I think it's going to be a PR disaster.
But statistically, there hasn't been too many launches like this. So there's plenty of risk, isn't there?
There is risk for the launch vessel itself. The capsule has independent rockets to pull it away in case of a problem, and it's got parachutes on it. So I'm less concerned about the capsule. I'm more concerned about just his health getting to the capsule.
And when does he go up? He goes up tomorrow?
The 12th.
The 12th.
So today's the
okay.
9th, 10th,
Wednesday.
11th, Tuesday. He'll go up Tuesday.
They already have a Russian actress up there and a director for 10 days making a movie. So he's not going to be an actor up in
Yes.
space.
He's not the first actor to go up there. So,
Yeah. So
but if you've ever seen him in public, he's a grade A, 100% ham.
he is.
Shatner? Yes, of course he is.
Yes,
He always has been.
yes. So, I've got a thing for electric vehicles, and for anyone that thinks there aren't too many models of electric vehicles out there for sale these days, and you can't just go buy one and stuff like that, or they're fancy versions of golf carts and stuff like that. There is an event happening October 16th and 17th. That's next Friday and Saturday. That is at Miami Marine Stadium. Not in the stadium itself because that's been condemned, but in the overhang parking area next to the stadium. They're going to have, it looks like maybe 50 or more vendor exhibits there of electric thing manufacturers and sellers. There'll be trucks, vans, cars, buses, scooters, mopeds. Basically, if it has batteries and an electric motor in it, you'll probably see one. But you won't see any of the big name companies there because they're just not ready yet. So you won't see Ford, GM, Chrysler, or Toyota there, which is kind of like, hey, that's telling. But what you will see is Tesla does not spend a dime on promotion. Every bit of Tesla promotion you see is from people wanting to independently promote it, or from things like Tesla car clubs. And the Tesla Car Club of Southern California will have a presence there. So you'll be able to see lots of Tesla models there. I don't know about drives. I don't know if you can jump into a Plaid and go 0 to 60 on a controlled driving strip or anything like that. But anyway, if you want to see the proliferation of electric vehicles, that would be a place to go look. Now, obviously, it's a for-profit thing and they charge for tickets and stuff. I haven't even looked at the tickets, but my guess is the tickets are probably around 20 bucks a head. Could be more, could be less, I don't know. But a couple of companies that were surprising that are going to be there is BMW, Hyundai, Kia, Jeep, which is a division of the same company as Chrysler, Mercedes, Mini, Polestar, which is kind of an offshoot of Volvo, Porsche, Volvo, and VW. They will all be represented there by cars. Some of those cars you will not be able to buy at the moment. They're prototypes. Some of those cars it's our first production model, and we were only going to make 20,000 of them over the next 2 years, and they've already been spoken for, all of them. So you couldn't get one even if you wanted to, because, we didn't make enough of them. So if a car company sets up a manufacturing production line that makes maybe 100 or a couple of hundred vehicles, that's probably a prototype run. If you're making more than 1,000 of them, that's a production run. And for you to make only 20,000 of them, that's a purposefully capped production run.
Like PlayStation.
Well, no, it's worse than that. You could be doing better, and you can actually get buyers that would buy it. But if you did that, then it would drag down your internal combustion engine vehicle sales, and you don't want that.
Oh.
So you can see the advertisements for the electric Cadillac or the electric Hummer or the electric Ford F-150 or any of those vehicles. They all look really great, and they're in production now with limited quantities, and all of them have been spoken for until 2 years from now when they decide if they're going to make more of them. I don't get that. The Tesla Cybertruck is not even in production yet, and they already have 1.5 million orders for it. And that's the vehicle that's so ugly nobody would want to buy it. So I don't get it. But the other thing about this show that seemed odd is none of the electric vehicle manufacturers from China are going to be there.
No.
And there are a lot of them. I don't think they're all actually vehicle manufacturers. I think they're electric vehicle manufacturers and parts suppliers. But the big names in China aren't going to be there, and that includes names you may never have heard of before, but they're big time. BYD, SAIC, NIO or NIO, XPeng, which is XPNG, Li Auto, Geely, and Chery. Those are all selling tens of thousands of units, and their productions are sold out, but they're willing to make more. And it was funny that BYD actually made a really small vehicle for the Chinese market. And it was so small that it was not considered actually a car. It was considered a cart. It had 4 wheels, it had batteries, it had an electric motor, but it didn't have, as in the US they say, sufficient brake horsepower to take it on the expressway. Also, by being in the cart class, it didn't qualify for the Chinese government incentives to sell electric automobiles. So what they did was they changed the size of the vehicle, they increased the motor, they increased the battery pack, and now that qualifies them for a $7,000 discount. And they took the $7,000 discount and used that to balance the offset of the vehicle. So now they have a legitimate car that there's a sufficient discount on it that they said, and we're going to charge you the same price as we did for the cart, even though it's a bigger vehicle with a bigger battery, with a bigger motor, and has longer range. It's in the 150-mile range, which is great for a daily commuter car. But that car costs $5,000 US if you were selling it in the US. And BYD is actually right now hiring sales and customer service representatives in the US. They plan on bringing that vehicle to the US marketplace. So that ought to be an interesting thing when people say, oh, these electric cars are too expensive, I need a cheap one. Well, they could sell it for $20,000 and be cheaper than any electric car on the market and make $15,000 in pure gravy per unit sold. So I think it's going to get crazy over the next couple of years. You're going to find that the big brand monikers that you would like to see there aren't going to be there because they've decided it's just not in their best interest. And their financial future looks bleak. Whereas the companies you've never heard of before, like BYD, they're going to be big time planet-wide and selling cars with the right mileage, with the right horsepower, and driving range and things like that. That just because you're selling an electric vehicle, it doesn't have to go 0 to 60 in 2 seconds. It can go 0 to 60 in 5 seconds and still be much better than your average internal combustion car.
Mhm.
So
Now, this meeting that they're having,
it's actually kind of a convention event.
okay, so they're having a convention.
Yeah.
This was probably planned a year ago or more.
Oh yeah,
right?
oh yeah. They actually have multiple cities, so it's a roving convention. I think the one after Miami is Austin, Texas. Coincidentally, Austin, Texas, near where Tesla is building a massive new plant.
Wow. Well, being that it's planned during the pandemic and that has affected development for a lot of companies, that they couldn't do production as they would have planned. Wouldn't that be impacting them also? They didn't just decide to have a show and not have anything to sell.
No, this is not a sales show. This is a demonstration show. So they're going to show you that these vehicles exist. They're going to show you their current street prices. They're going to show you that they're in production now. They're going to give you information on the companies, maybe places where you can go buy them. So it'll be informative, but you won't see your local Chevy dealer at this event.
Well, that's sort of a nice thing, isn't it?
It's not nice for GM.
But I mean, because you're always feeling like when you go to some convention that somebody's trying to sell you something and that you're not there just to learn about it.
Yes,
Sort of-
that will be good. That will be good. But I'm sure that there will be some companies that are there that don't get the message that it's a demonstration show, and they will try to sell you things. Come on, it's only $500. Don't you want to buy an electric bicycle? We got them on sale.
They have three-wheel vehicles, three-wheel electric vehicles. I've ridden one. And it's really nice.
Yeah.
And it's
Well,
street
They,
ready.
they actually have those in Europe because you're allowed to drive those in the inner city areas because there's no highway performance and braking requirement.
Well, you can drive them here too, on the street. They go
I've seen the ones that
60
are,
miles per hour in 5 seconds.
I haven't seen the electric version of that. I've seen the internal combustion engine version of that.
Oh, no, I drove an electric one.
Oh, okay.
It was
You
good.
remember the brand name?
No, it's up the street from me. And it only costs a couple $1,000s. And I go, wow, that's not a bad price.
Well,
Pride
that's
rings the bell.
that's the thing is that once you learn about an electric vehicle, you'll realize that there are several hundred parts fewer to an electric vehicle than there is to an internal combustion engine vehicle.
Yeah.
And this week, Tesla announced that
It's
in
Polaris.
Shanghai, using their GigaPress, they are now making the entire back-end chassis and front-end chassis as 2 cast aluminum alloy pieces, which is literally, they've removed a lot of robotic welding from the production line, which will allow them to crank out the cars faster.
Mhm.
And it makes the car several hundred pounds lighter because they don't have to use as much steel and welds. And therefore, the cars are expected to get better range, better acceleration, better handling. They just keep improving. By the way, did you know they sold 240,000
Solar
Tesla
one.
vehicles last quarter? I'm sorry, sold is the wrong term. 240,000 were delivered to people.
Wow.
So when you don't think companies can make a lot of these electric vehicles and sell them and get them to people, there's 240,000 reasons why that's a false impression.
Yeah, I know somebody is on their second one.
Yeah.
I love it so much.
Well, they are expensive, and the odd thing is, right now for certain models, you wouldn't be able to get them until April or March of next year because they've got a backlog. Despite making as many as they can physically make, they've got a backlog. You can actually place on order for delivery in early next year a Tesla Model 3 or Model Y at a cheaper price than you can buy a used one, because the people that have used ones are actually charging you more for their used vehicle than for the new vehicle, because that's what the level of demand is.
How do these cars hold up for mileage? I mean, like, like they say.
What do you want, 1,000 miles? How many
200
miles do you want? Do you want
Okay.
200? In general, they all do 200 nowadays. You want 300? I'd say probably half a dozen of them are doing 300 plus.
Well, they have some that have solar panels, some cars that have solar panels on the top now.
Yeah, but you're going to get a lot more power out of a wall outlet than you will out of a solar panel.
Yeah.
And
It's more like to keep the air conditioner and, electronics inside charged, but not really charged to the distance. Now, what is good is stopping the charge while you at work and your car is parked.
well, there are corporations and there are hotels and convention centers that are actually putting in charging stations at their buildings, so that if you happen to be an executive who can afford a Tesla Model S or Model X, you can charge up at the office.
Well, the Galleria has been having Tesla charging stations for
Yes.
years now.
I've seen them around, yeah.
Well, at one point, the Galleria actually had a limited demo center for Tesla. They haven't had one for a while. The Boca Town Center still has one. They're not sure how long it's going to be there. When you've got that much demand, why are you spending money to show it off. People already get the idea. People are already buying it.
Yeah, but I bet they might have like a little a counter there for you to sign up to the list.
Oh, you can do that online. If
Yeah.
you're interested in buying a Tesla, I think you've heard of the internet.
I ate my Tesla.
Uh-huh.
I think there's a deal that Tesla makes with their charging stations where you can like charge up for free or something.
Well, it depends upon which model you buy. If you buy a top of the line Model X or Model S, you get free charging for the life of the vehicle. If you
Yeah.
buy a Model 3 or a Model Y, you can buy a certain amount of charge over a multi-year period. So, you know, they'll charge you less than if you just went in there and bought the electricity retail. But by far, the cheapest place to charge your Tesla vehicle is your house,
Mhm.
because there's no revenue margin in it. You are paying what you're paying, and you're paying residential prices. Electricity at commercial sites is far more expensive than it is for homes, for residences.
Don't
So
you have to put a port in or something in your home?
if
Oh,
you
yeah.
don't mind topping it off overnight whenever you get home, you don't have to make any modifications to your house power at all. There's an
Oh.
adapter that comes with the vehicle that allows you to plug it into a normal 15 amp outlet, but it's going to take a while to charge it up. So don't drain it down to 20% and then expect to recharge it to 100% overnight. But for only a couple of $100, you can buy a device that you plug into a 220 50 amp outlet, like as if it's a water heater or an air conditioning unit. And you can get the same level of charging that you would at your typical commercial charging station. So then you can fully charge your vehicle overnight. If I owned an electric vehicle, I would certainly invest the couple $100 to put in the outlet in the garage and then plug the car into that. But then I have a garage. Some people don't have a garage.
Yeah, isn't there a couple different types of charging? So,
Yes.
you know, people that have electric cars can't necessarily use the Tesla charging stations.
There's been recently a government proposal, and it's part of the current Infrastructure Act that they're
Yeah.
trying to get passed by Congress, whereby Tesla will agree to have a certain number of its charging stations open to non-Tesla vehicles. Now, the non-Tesla vehicle owner will have to buy a power adapter. It's just a smart adapter plug. And you will be able to charge up your non-Tesla vehicle at about 80% of the rate than if you were a Tesla vehicle. And you will pay, I think they were saying it's a 12% premium over what a Tesla driver would pay. But all of a sudden you get access to several thousand charging stations spread across the US that you wouldn't get if you were limited to just using the Volkswagen-based Electrify America solution.
So it's true.
And also the Tesla charging stations are fully monitored for their usability, whereas some of these third-party charging stations aren't. How many times have you gone to a gas station where the tire air pressure pump was not operating? It's because they outsource it. Well, if you happen to go to a parking garage where your residence is located and the car charging station is not working, it's because the building just outsourced that to some vendor, and the vendor only makes money if people charge. And if people don't charge often enough, they don't make enough money, it's not worth it for them to come out and maintain the charger. So they just let it die, and you'll be low on power, and you'll drive up to it and it'll be non-functional. And you'll call them up and they'll say, we'll have somebody out there next Tuesday to take a look at it. Like, that's not service. So that will give electric vehicles a bad name. But I don't think Tesla thinks that way about it. I think they look at it and go, okay, we've seen a lot of people driving from this point to this point, and we know what their charge levels are So let's give them a break. Let's put another charging station in between those 2 points. And they've done that along all the major highways in the US. So if you're going to be on an interstate and there's a rest area, chances are it's going to have a Tesla charging station there or at the next rest area.
I think I saw a guy talking about machine language and how within the next 20 years, you won't buy a car anymore. You'll just simply
Yes.
call for one self-driving car to pick you up and take you wherever you want to go.
Yes. There is already a company that's doing that. They received some funding from Amazon and some funding from General Motors. The company's name is Waymo, W-A-Y-M-O, and they are working with Rivian, I think it's Rivian, to produce electric vehicles that are fully autonomous. No driver, no steering wheel, no accelerator, no brake pedal, no rear view mirror, no outside mirrors. You'll use a Waymo app, kind of like an Uber, and you'll say, hey, I need a vehicle at this address now. And they will dispatch a fully autonomous vehicle to that location. You'll jump in, it'll take you to where you told it you wanted to go.
Right.
You'll get out to go do your grocery shopping or whatever. The vehicle will disappear. It'll go pick up somebody else. And then when you come out with your groceries, you'll call up Waymo again and say, I need a Waymo to take me home. And it'll remember your house in your account. So it'll know where your home is. So you'll, throw your groceries in the vehicle and it'll take you home, and then you'll release the vehicle again. That will be a game changer. And I can see it happening in the next, you'll probably see starter programs in the next 5 years, but I would say in the next 20 years, it's going to change the shape of transportation throughout the world.
Well, there's a lot of big cities already that they're doing that, but you drive your car, so you need a driver's license. But you go and you have your card, and your card activates, or your phone activates the little machine that has in the window. It opens the car for you to drive. You drive, so you have an app showing the locations of the cars that are not in use, and then you drive around and do whatever you need. You pay up and leave your car, whatever is convenient for you, and somebody else come to pick up. So it's like in large cities that already people don't own a car anymore.
Yeah, and that's a stopgap. The moment that they realize an electric vehicle does not require all the service of the internal combustion engine vehicle, that will be the transition for them to go fully autonomous. Is you don't have all the maintenance, you don't have the fuel costs, and even better, you don't have silly humans behind the wheel that can cause accidents, which keeps insurance rates up.
Yes.
So are the insurance rates down?
If you buy a Tesla, you can actually buy your automobile insurance from Tesla for several $100s less per year.
Wow.
Because Tesla is insuring their own vehicles, because they know that when given the opportunity, Tesla drivers will turn on the autopilot or will have bought full self-driving. And that makes the probability of an accident far less.
Yes.
So if right now you own a vehicle, and if you have to make monthly payments on it, and you have to pay for gas, and you have to pay for maintenance, and worse than that, you have to pay for insurance, and it depreciates. If you can get rid of all of that and still have access to a vehicle on demand for normal travel, you're going to do it.
Yeah.
Would you be scared to get into one of those autonomous cars?
Not at all.
Really?
Not at all. Are you afraid to get into an airplane that has an autopilot?
Well, there's a guy standing
did.
sitting right next to it, though.
Oh, really? And what happens when he comes and he starts walking down the aisle greeting the passengers?
Yeah.
Right.
There's some rule, isn't there? Somebody's got to be up front.
Yeah, the co-pilot. Oh, they got rid of the navigator because they didn't need him. He was costing too much money. So when they make these airplanes, when they make these airplanes electric, the next step is going to be, why do we need pilot and co-pilot?
Yeah.
Autopilot
but there's a limited
does most
amount
of
of
the work.
stuff that, how much can you hit up in the sky,
Well, here's the funny thing.
Bird.
whenever you see the airplane land and do one of these weird ass crab crawl landings and such,
Yeah,
there's no pilot landing that plane.
yeah,
When
yeah.
you
This
see a
plane is too
plane
smart.
landing- When you
Smart
see
plane.
a plane landing in complete fog, you can't even see the runway, or it's pouring down rain. You can't even see the runway. The pilot's not landing that plane.
He's got a moth equipped with a lightning bug.
No.
Monroe, where have you heard that? Because
Where?
you have to have 3 miles of visibility to land. That's why they don't land when there's fog.
Really?
Yeah.
You might want to go out on this little place called YouTube and look at videos of commercial airliners landing in complete overcast.
Mhm.
Totally can't see anything. And they have
Because
to
I've
use,
always heard you got 3 miles of visibility. That's why
No.
they close airports. But the pilot is in between. When he goes down and greets the passengers, he can be an autopilot or he has a co-pilot sitting there. But
yes,
the
I
plane
agree
doesn't
with
take
that.
off and land by itself. The pilot. Okay. And crosswind landings, the pilot has to fly in a crosswind. When you see planes coming in at an angle, they're counteracting the wind.
Oh, I
That's
understand
why
the
they come at an
concept
angle.
aerodynamically,
Mhm.
but the level of precision required to do that on a fly-by-wire plane, yeah.
Well, I remember how terrified people used to be to get into a choo-choo train. It's one thing to ride on a horse or a
Oh,
wagon.
yeah,
drawn by-
it's gonna hit stuff. It's gonna run off the rails. Yeah.
it
And they
was
do on
scary.
occasion.
People would be scared out of their gourd to get into a train.
Yes, in another 20 years, people will be frightened if somebody sits behind the wheel, if there is a wheel.
Yeah. That's right. Well, I look forward to that because that's about the time that I don't want to buy a car anymore.
Well, I look forward to it as that's about the time they'll jerk my driver's license away from me.
Why? Why would they do that?
Oh, I don't know. My vision goes bad. I'm not mentally all there. Yeah.
16 million tickets.
Oh, you're laughing because I'm already halfway there?
Takes a while to get you there. Believe me.
Yeah. Yeah.
That's a thought. Yeah. That's a thought.
Okay, enough about the electric vehicles. I'll give you an update on my numerous projects. You remember my cylinder that has all the little grooves in it for the antenna? Well, I started playing with how to make the metal to go into those grooves. And I started with some heavy gauge metal, and that didn't go well because it didn't take the bending. So I got some aluminum wire, and also that didn't go well. It didn't take the bending. It wouldn't stay in position. So then I went to lighter gauge stuff. I said, this is copper. It's calling it soft copper, pure 100% copper. It's stiffer than the aluminum. So I said, well, let's go for the throat here. I've got some solder, which everybody thinks solder is really soft and it bends easily, but it's still just a bit too stiff and you can't bend it tight enough to fit into the corners. So I said, well, let me get some finer rosin core solder. Now this is too far, that's too small. And you bend it in and it just pops out. So what I'm thinking about doing now is they actually make PLA filaments for 3D printers that are magnetic, conductive, and more conductive. So they take the plastic and they mix it in with powders of iron, copper, and carbon fiber. So I'm looking at getting a 3D pen. They make what looks like a pen, looks kind of like a glue gun, and it takes a filament of plastic in the back, and then you push a button and it squirts out hot plastic. And so I'll just take the cylinder and I'll squirt the conductive or magnetic hot plastic into the grooves, and it will seal itself into there. So
I've seen those pens on
Okay.
Michael's with the kids.
yeah,
They make like sculptures that are
Yep.
3D.
yeah, you can get those. You can get those for under $20, the low end ones. But the one I'm looking at, I want it to have a metal nozzle because I'm going to be using stuff that has metal powder in it, and that's very abrasive to a plastic nozzle. And I want one that can get hot enough to print ABS plastic. So it's going to be hotter than PLA. And I want one that has a retract button so that when I get to the end of something, I can literally suck the filament back and it won't like leave stringy stuff. So this one's probably going to be in the, certainly under $100 range, but more like in the $60 to $80 range. So there's that, and there's the other thing. Remember, this is the starting point, a cylinder. What I really want to do is make it so that the narrow end actually comes almost to a point. So it's a geometric surface called a frustum. If you think of a cylinder and then you squeeze it down until it's a cone, and then you whack the top off the cone at right angles, that's a frustum. And we'll get into frustums shortly. So, and last week's session, Mars Perseverance and Ingenuity Update has been posted to the YouTube site. In case you missed it last week and want to see it. I edited it down from a little over 2 hours to right at 2 hours. There wasn't a lot I could cut out. But tonight we're going to talk about the EMDrive and Photonic Propulsion. The EMDrive, some people may have heard of. Photonic Propulsion is something I coined several years ago when I started reading about some research scientists going back all the way to from the late 1800s into contemporary stuff. So we'll talk about both of those. Okay, so welcome. And tonight we're going to talk about the EMDrive and Photonic Propulsion. So I'll give you my opinion right up front. I don't believe the EMDrive makes use of or requires quantum vacuum energy, something they fell back on when it didn't produce the results they want. And I'm not aware of the means by which you would use quantum vacuum energy for propulsion. So just, that's not a part of the picture. So if you think that it's all spooky science, quantum vacuum energy and quantum mechanics and such, it's not. So I am not a promoter of the EMDrive as it currently exists, or its attempts at doing propulsion using an identical design approach and specifications. The EMDrive as it stands is in strong need of a redesign, and we'll get into the details of that. And then they also have to optimize its performance. I do believe that radiation reflection pressure as a physical force exists. It has been researched and peer-reviewed by noteworthy scientists, starting with a little guy named James Clerk Maxwell. Some of you who understand physics will know about him. It's been proven to function in a vacuum. It's a force used in applications from spacecraft to electron microscopy today. There was actually a Nobel Prize awarded for the use of the principle. Solar sails make use of the principle, and the James Webb Space Telescope will actually make use of it to stabilize its position in its halo orbit around the L2 Lagrange point. Radiation reflection pressure, to my knowledge, is a force yet to be optimized for spacecraft propulsion. I've done a lot of looking and have yet to find any private or public projects from NASA, the European Space Agency, the Japanese Space Agency, the Canadian Space Agency, and the Chinese Space Agency. So they can see that it exists. For some unknown reason, they're just not connecting the dots, and I just don't get that. So the limiting factor of today's propulsion solutions. For those of you with basic physics, you've heard of Newton's third law, or F equals ma. Basically, if I throw something out the back of my rocket, I'll go forward. If I throw something heavy out the back, I'll go forward faster. If I throw something out the back faster, I'll go faster. That's where you get the mass times accelerations equals force. And that's how rockets work, including ion propulsion. So all the propulsion you've ever heard of for rockets, nuclear, all of them, they're all based upon Newton's third law, F equals ma. But it's a limitation in that if you have a fixed fuel supply, when you're out of fuel, you're at end of mission. even though your spacecraft electronics and solar panels and everything are still working just fine. You just don't have the fuel required to keep yourself in your orbital position. So you have to push your satellite or spacecraft off somewhere else, or crash it into something, or just let it, deorbit, or, stay in a long duration orbit around the sun or around the Earth. The only other thing that you have access to are what they call momentum transfer devices. These are gyroscopes or momentum wheels. They're spinning wheels that if you apply a magnetic field to it, the momentum of the spinning mass will actually move your spacecraft in orientation. It will not accelerate it. It will not decelerate it. It will literally just rotate it in some angle. So all the satellites that are up there right now, they basically have an end of life based upon how much fuel they put in the tank at liftoff. And when they're out of fuel, they can't go any farther. SpaceX has actually realized this to be a shortcoming. If you look at their mission description plans, if they want to go to the moon, what they're actually going to do is launch a ship into Earth orbit. Then they're going to launch a fuel tanker into Earth orbit. Then they're going to be doing fueling of the original spacecraft in Earth orbit that will give them enough fuel to get to the moon. Then they're going to launch a fuel tanker to the moon so that when it comes up from the moon, it can refuel itself to get back to Earth. So they're literally putting in Earth and moon gas stations for these, fuel-based rockets. It's just what you do if you're running on a fixed fuel tank. So you're given a fixed amount of fuel at launch, and this is the Achilles heel of your mission duration. So if you look at any space probe and you see that it's good for 5 or 10 years, it's not because the electronics are going to wear out. It's not because the orbit's going to decay and it's going to fall back. It's because it runs out of its fixed supply of correction fuel. And even though it has electrical power, as solar panels or an RTG, radioisotope thermal electric generator, once it runs out of course correction fuel, it's not controllable anymore. So all the missions that are of longer duration either were solar powered in a stable long duration orbit like a geosynchronous, or we're in open space with an inertial coasting trajectory, and they're powered by RTGs. So Voyager 1 and 2, they have no need for course correction. They just identify their course to NASA's Deep Space Network, and we move the antennas rather than expecting them to change the direction they're going. Now, obviously, they still have to orient themselves, and for that they use gyroscopes or momentum wheels. But once those give out, they won't have the ability to point back at Earth. So even they will be at end of mission. There is research in how to make spacecraft last longer. And you can see this in, for example, the SpaceX satellites that they put up. They use they use krypton gas ion propulsion rather than liquid fuel. They use ion propulsion. And there have been spacecraft that use ion propulsion that was xenon based. The reason why they switched to krypton is krypton's cheaper. Even though you have to accelerate the krypton ionized particles faster because they're lighter weight than xenon. But they went with krypton because they want to put 1,000+ satellites up there. That fixed amount of gas under pressure is still going to cost you something. Ion and other forms of propulsion, none of this is related to faster than light travel, which is what is required for interstellar missions. So limited force propulsion is useful. Even if your propulsion solution can only give you tiny fractions of a Newton of thrust, that's useful. And if it weren't useful, you wouldn't see things like NASA spending money on ion propulsion, SpaceX spending money on ion propulsion. Even though these things are just a small fraction of a Newton, if they can leave them running for a long period of time, the acceleration will build up. They're still F equals ma based. They're still, throw it out the back, throw it fast out the back if it's smaller, and that's their means of propulsion. But if you're using a compressed gas, you can spit out very small amounts of it with valves and plumbing and heaters and such, where it allows you to run your engine, your propulsion source, for hours or days or months. So the best ion propulsion system that's out there today is the NASA NSTAR, NSTAR. And at long duration propulsion mode, when it's not running at full throttle, the most it puts out is 14 millionths of a Newton of thrust. And that was enough to get to, objects in deep space over years of time and to move from one object to another. This was first proven on the Deep Space One probe, and they realized it was sufficient. So the Dawn spacecraft actually had a couple of NSTAR engines on it. They were going to initially use them as backups because they didn't have enough faith in the design that it would last that long. So they paired them up, but then they later on used them as course correction maneuvering, even though Dawn also had hydrazine-based liquid fuel for course correction because it needed greater thrust for orbital insertion and extraction. But the reason why Dawn went to end of mission is because they ran out of hydrazine, not because it ran out of xenon. If you want a spacecraft to operate for 10 plus years, if you were to use an ion propulsion system and were to attempt to run it at maximum propulsion, its propulsion would only last for a matter of hours, less than 1 day, because the only way you can put that much out the back is if you put it out under high pressure. And if you put it out under high pressure, your tank is going to be empty much faster than months. It's going to be less than a day. So when they want to run the ion engines for extended periods of time, they run them at a small fraction, usually about 10% of their total output. So 14 millionths of a Newton was more than enough thrust to make Deep Space One workable and to make the Dawn spacecraft practical. So there's this thing called the EMDrive, Electromagnetic Drive. It was to create a new form of electricity fueled propulsion, not using any chemistry. I guess you could say, well, ions are chemistry, photons are chemistry, but they weren't combusting anything. They weren't ionizing anything. So this would be different than any other form of propulsion that exists today. Its power source, if it was photovoltaics within range of the sun or RTGs, would be limitless, which means its propulsion would be limitless. It would be far less complex, far fewer parts, reduced electronics, smaller, lower mass, faster, cheaper. It's all the right stuff to make it the better solution. A fixed fuel tank would no longer signal the end of a mission for an otherwise functioning spacecraft. All were admirable goals, very beneficial if they were just successful. So if you've never seen one, here's a little history of the EMDrive. The generic description of the EMDrive is it's a closed loop radio frequency resonant cavity thruster. Closed loop means the radio energy does not get out of it. That's its first problem. It's a resonant cavity thruster. They were using microwaves. If you want resonant microwaves, it needs to be very much larger. In 2001, Roger Scheuer created the EMDrive, and then later on, another alternative of it called the Cannae drive by Guido Fetta over in Italy, attempted to reproduce it. The Cannae drive claimed to produce the same effects as the EMDrive, but it was within the, I guess you could say, less than 5 nines of accuracy, and considered it, NASA considered it noise, but it was obvious enough that they should take a look at it. So there's a group within NASA called Eagle Works that plays around with these edge things. So they created something similar to what the EMDrive was, I don't know why they did this, but they created it with, instead of a frustum shape, it's a stepped frustum. On the right, you can see that there's kind of a cylinder sitting on top of a cone. I don't get what that's for. These were shoestring projects. So the reason why you see all the bolts there to hold it all together, microwaves are not under intense pressure. They held it all together with bolts because who can weld? This is a shoestring project, but it's a lot easier to just drill holes in the metal and bolt it all together. So on the left, you'll see the basic concept of an EM drive. The idea is you have a magnetron, kind of like a microwave oven. You have a magnetron that produces microwaves. They inject the microwaves from the side. The ends of the frustum are capped, and you have the microwaves bouncing all around inside the frustum, and supposedly it will concentrate them on the smaller diameter end. And by having fewer bouncing microwaves off the smaller end, that will make more bouncing microwaves off the back end. So that will kind of act like an F equals MA drive. But that's not how radiation reflection pressure works. But we'll get into that in a second. So they couldn't reproduce a sufficient amount of even nanonewtons of thrust to claim that it was peer reviewed and reproduced. So NASA's kind of set that aside. However, the China Academy of Space Technology, there's a scientist there who claims he has a variant of the EM drive aboard the Chinese space station and is undergoing testing. But I have no pictures and no details of what that thruster looks like. But if they're just using it to orient the Chinese space station, even a fraction of a Newton would be more than enough to prove the physics concept. So maybe we'll see something from them in the future, but I don't have any details at the moment. This was back in 2016 when they first put up their space station. So here's radiation reflection pressure. There's a picture over on the right. And the idea is that if I have a photon and the photon reflects off of a surface at an angle, that it transfers momentum to that surface. It doesn't so much produce a force in the direction of the photon, it produces a reaction force in the opposite direction. So you remember me saying that if the EM drive were really using radiation reflection pressure, it wouldn't be throwing thrust out the back, it would be transferring momentum towards the front. So it would move forward towards the small end, not away from the back end. So radiation reflection pressure is a proven fact of physics. If you doubt it, please do read further before critiquing it. It doesn't produce propulsion by tossing accelerated mass out the back of the spacecraft. It does not deny Newton's third law. That still exists. It's not counter to it. It just doesn't utilize it in that way. It doesn't throw photons out the back hoping that that mass will be significant. It does not deny the conservation of momentum. In fact, it actually uses conservation of momentum to transfer momentum from the photon to the surface reflecting off of. So it counts on momentum transfer. It doesn't rely upon unproven physics. There's no 0 point energy. There's no vacuum energy. There's no quantum vacuum energy. It's very basic physics. I mean, after all, they first looked at this in the 1800s. So not a lot of fancy technology back then. In fact, there was no quantum physics back then, in the late 1800s. In the early 1900s, yeah, quantum physics. So when a photon reflects off of a surface, it transfers momentum to that surface. And there's a long history of people researching this, starting in the 1800s. That's when Maxwell was playing with it. But Maxwell didn't have any of the newfangled technology. Like back then, he didn't even have silvered mirrors. When he first started playing with this, his mirrors were polished metal, which are only about 80% reflective. So two guys named Nichols and Hull, they first proved that it actually transfers a measurable momentum in the early 1900s. And then in the late 1920s to early 1930s, two other scientists named Bell and Green confirmed it, measurable repeatedly in a vacuum. But even Bell and Green had constraints in their day. There were no LEDs. The best they had to offer was incandescent light bulbs, which don't produce a lot of photons. The flux density, how many photons per square millimeter, was very low. You know, what we've got today, we can do much better with. Radiation reflection pressure was actually used on the Kepler-2 mission when they had a momentum wheel go out on them. They actually used the force of the sunlight from the sun, the solar wind, to push on one side of the spacecraft, and they used a reaction wheel to push on the other side of the spacecraft to stabilize its orbit so they could continue to do observing for a second mission. In 2018, there was actually a Nobel Prize in Physics awarded to a research scientist who created something called optical tweezers. What they did was they used very low power lasers to push things around inside of the slide of an electron microscope. You're not going to get a probe in there small enough to push around as an individual bacterium or virus. So what they did was they used lasers to shine light off of them and push them around, and that won him a Nobel Prize in Physics in 2018. So it's proven, it's practical in equipment. The James Webb Space Telescope is flying what is known as a halo orbit around the L2 Lagrange point. And on board the JWST, there is a large black foldable vane. It's just a big flat piece of aluminum that has, you know, it can open larger or be smaller, and it can tilt. And what they're going to do is when they want to stabilize the position of the spacecraft and they don't want to run up the reaction wheels, they're going to use the pressure of solar wind against this panel of aluminum to keep the spacecraft in position so they can do their observing. So once again, it's proven in physics and it's usable. So what wasn't available back when they were first researching this? So I've already mentioned that Maxwell, the best he had to deal with is polished metal mirrors. He was in the late 1800s. He didn't even have electric light. He used the sun and lenses as his source. You know, we produce much better lenses nowadays. What he didn't have available is high output near ultraviolet LEDs. He didn't have silvered mirrors, let alone dielectrically coated mirrors. So he couldn't produce a lot of force, weren't a lot of newtons, but he did work on the kinds of balance scales or balance beams that would allow you to measure small fractions of a newton. So in the early 1900s, Nichols and Hull looked at this in a little more detail to evaluate the wavelength of light and how that has an effect on it, the angle of incidence and reflection and how that has an effect on it. But the best they could do was arc lamps. And if you know carbon arc lamps, they're extremely bright, but they're also not a continuously uniform light source. They're very, I don't want to say sparkly because they're not burning metal, but they're not continuous. They're not solid light. But what they did have was silvered mirrors, but they were early silvered mirrors, so not as good as what we have today. Once again, no high output near UV LEDs, no dielectrically coated mirrors. So in the 1930s, when Bell and Green published their works, they did peer review against what Nichols and Hull did, and they actually confirmed it in vacuum. So it's not your Crookes radiometer, little black spinning vane thing. It's actually a different physics principle. But Bell and Green could use tungsten filament electric lamps, but even they didn't have a high output UV LEDs, and they didn't have dielectrically coated mirrors. So they're still down in the low 90s reflectivity. Here's why we can do it today better. So if you actually go in and look at the works of these scientists and they confirm that the physics principle works, here's what we have today that will make it so much more force than what they had. I mean, it's not going to be a Saturn V, obviously, but it'll certainly be on par with what an ion engine produces today. So dielectrically coated mirrors first came about in 1937. That maximizes the reflectivity of the mirror and the uniformity of the reflectivity of the coating. Circuit onboard surface mount device LEDs, where you could pack a bunch of tiny LED emitters into a very small number of square millimeters, those didn't exist until 2010. So these very, very bright output LEDs, where you can get, a 50-watt LED for 20 bucks, and it's about as big around as the width of your finger, and it produces 50 watts of bright white, and you don't want to look at it because it's brighter than sunlight. Those didn't exist until 2010. Prior to that, you had individual LEDs, like a little piece of plastic with 2 wires hanging off of it, and the best you could get those up to was, maybe 30, 50 milliwatts, whereas today's COB SMB LEDs, you can get those suckers up to 100 watts. And I've seen commercial prototypes online of 500 watts. And you're talking about 500 watts of LED output in an area the size of a postage stamp. And these aren't lasers, these are just LEDs. The high lumen per watt LEDs didn't exist until 2014. They changed the chemistry of the LEDs from their gallium arsenide. They put in other elements in the mix, and they actually got more output for a given amount of watts input. So when you see something says it's a 3-watt LED, you don't actually get 3 watts of light out of it. You get about 1.4 watts of light out of it for the 3 watts you put into it. The rest of it becomes heat. It's just the inefficiency of solid state electronics. I'm hoping someday we'll figure out how to do better. And this one, which goes directly into some of the discussion of the shorter the wavelength, the higher the energy, and therefore the more momentum transfer you're going to get. Royal blue near ultraviolet LEDs did not even exist until 2016. These are monochromatic, very narrow band royal blue, and they're very high output. They're so bright you don't want to look at them, and they're only 3 watts. And where all this came from is, yes, you guessed it, Blu-ray, because Blu-ray laser discs don't have Blu-rays in them anymore, haven't had lasers in them for some time. They have these bright blue near UV LEDs because they're cheaper. So as technology has a need, it creates a solution and things roll forward. Well, if you're like me looking at all this stuff, you can connect the dots and go, I've got a better mirror. I've got a higher output, smaller surface area LED. I've got higher wattage for power going in, and I can get it closer to UV to get more energy out. So that's what we have today. It would make it, now's the right time. So how to maximize the effect? If you want to maximize the amount of momentum transferred from the photons you're emitting to your reflector, here's what you can do. Photons of a short wavelength transfer more momentum. So don't look for microwave, because that's really long wavelengths, really low energy. Don't go for infrared or red. Don't go for white, because that's too broad spectrum. Go for those near UV. And I will say, don't go all the way to UV, because UV has its own problems of reflectivity on surfaces. So if you can get almost to UV, that's where you increase the energy, shorten the wavelength, and transfer the momentum. The emitter needs to be highly efficient. So you don't want to buy a cheap LED emitter that doesn't put out many photons. You want the maximum amount of photons per input watt of power. The number of photons per square millimeter of emitter should be as high as possible. The amount of photons per square millimeter is referred to as flux, but it's not a flux capacitor, it's just flux. Sometimes you'll hear this referred to as lumens. The problem with lumens, and there's actually an ANSI standard, international standard for the measurement of lumens. Lumens takes into account the physiology of the human retina. So it's actually skewed. So when you look at something and say, how many ANSI lumens is that? Oh, that's bright. Well, that's bright to the human eye. It may not be as high energy as you think, because the human eye is more sensitive towards green, and therefore the amount of output in green is higher with high ANSI lumen LEDs, because that makes it where people can see it better. But in this case, you don't care what, whether people can see it or not. You want them to be highly optimized for reflection. So don't worry about the lumens, worry about the particular wavelength and then the energy in to energy out. And the thing that you're using for your reflection, you want to be 99% plus reflectivity, and you want it to be a uniform surface. So you want a sputtered electroplated surface, and you want the surface to be ultra smooth. Even aluminum oxide would be a good smooth surface, and then you can coat that. So that would be your mirrored surface if you want to maximize it. And the reflection angle should be oblique, should be very shallow. Now, if you're doing this with the photons against the reflector, that actually reduces the amount of energy, the amount of momentum transfer to almost zero, very small. But if your surface is like this, and the reflection of the photons is off of it at an oblique angle, you get a much greater transfer of momentum to that reflector. Do not create a reflector such that your photons reflect at 90 degrees. When they get to be 90 degrees, let those photons go out the front. Don't try and hold them in. It's not a closed loop. It's better if it isn't a closed loop. That's one of the failings of the EMDrive is it's closed on both ends. When you stir up all the photons, where are the inefficiently reflecting angle photons going to go? And you don't want the photons to roam around randomly reflecting, because then that doesn't concentrate all the maximized reflection angle in one direction. And you want to turn off and on your emitter with very, very short high energy pulses. This is a thing called shot noise. Think of it this way. If you hear a piece of metal getting rained upon, you don't hear a continuous sound. You hear kind of a pattering of raindrops. That's because not all the raindrops are arriving at the metal at the same time. So if you want to transfer the maximum momentum, you want all the photons hitting the reflector at as close to the same time as possible. And the way you do this is you don't turn the emitter on and just leave it on. You make very, very short, high energy pulses. And you can pulse that as rapidly as you want, but you want to make the time as short as possible so that all the photons are almost laser-like lined up so that they all whack it at the same time. And if you want to know the difference between raindrops on a sheet of metal and a fire hose on a sheet of metal, that's what you're talking about. So what the EMDrive got right, and the first thing to notice in this picture is this is an original EMDrive that NASA took in for evaluating before they came up with their own design. Notice it's purely a frustum. There's no cylinder on the front of it. So this is a very early attempt. This is a non-stepped frustum. This is just a straight frustum. But you can see the connector there on the side. They're going to inject the microwaves from the magnetron into the side of it. And you can see the plate on the front and the back. So once you inject the microwaves in, they just crazily bounce around inside there. And you're hoping that the fact that you've shaped it as a frustum is a differential means of producing force. But by having them reflect at 90 degrees and convert into infrared heat, you're actually negating what force you're producing, which maybe it'll produce, a couple of nanonewtons at best, but you could probably write that off to the energy traveling through your RF coax cable. So what they got right is radiation reflective pressure for propulsion. Good concept. Chamber is reflective of the injected radiation. Well, they're injecting microwaves, so they made it out of copper. Okay. They made it frustum shaped. Okay. but design was expected to achieve greater propulsion than it actually did. Its failing is justifiable. So here's the laundry list of what they got wrong. So had they produced a greater level of force, there would have been more easily peer reproducible results. So lacking that, the whole concept was found unacceptable during peer review, because if you're down in the 1 or 2 nines of reliability of your data, it's not proven science. You need to get to 5. So I get it that both Scheuer and EagleWorks were operating on shoestring budgets and kind of building, cobbled together things. But when it didn't work out their way and they hinted at unproven science, like it's an example of vacuum energy, that didn't help their case. So between their shortcomings and the unproven hype, this is how it got labeled the impossible drive. It's not impossible. It's just a bad design, but it could be improved. So had they had a stronger understanding of the foundational principles of radiation reflection pressure, they probably could have solved their issues and built something that would have been better. So I just think of it as they need to do their homework and read more about Nichols, Hull, Bell, and Green. So the design had inefficiencies. The wavelength was microwave. That's way too long. There's way too little energy being transferred in reflections. And I actually calculated that out at a per photon basis. These are very small numbers, but this is just per photon. And there's enormous numbers of photons when you turn these emitters on. So let's just think of it as if I compared the momentum transferred by a single photon of microwave versus royal blue wavelength, here's the difference. And you can see, well, if you don't know scientific notation, you'd think 6 is more than 1. But if you look at the exponent, you'll notice it's minus 28 versus minus 27. And this is joule seconds. That's a derived standard unit of measure for force. So their emitter should have been a 3-watt royal blue LED and not a 2 kilowatt RF transmitter. You can actually get more momentum transferred in royal blue at 3 watts than you can by randomly reflecting 2 kilowatts of microwave energy. Also, going with an LED as the photon source would have made the whole assembly much tinier, lighter, not as big, not as heavy, and much easier to calculate the sub-unit Newton thrust. Also, the ratio between the wide base of the frustum and the small apex of the frustum should have been much larger, more conish, less stubby. And they need extreme reflectivity. I don't know how polished their copper interior was of their reflector, but if you have a dielectrically coated mirrored surface, you can obviously reflect more photons. And if you're doing this at the royal blue wavelength, you're transferring far more momentum.
Yeah, and in the case of microwave, that was reflective enough.
Yes, but they also had seams. If you saw the seams where they didn't weld, they bolted on the front and back covers. There was a lot of leakage through that. Also, the microwaves came in from the side as opposed to the rear. So they had literally no control of the reflectivity of the microwaves inside the chamber. And the wavelength emission should be short duration pulses rather than just turning on the magnetron and letting it run, which is what they did. So there were a couple of downright contradictions to producing their desired result. The first is, as I said, side entry, non-optimal reflections, and they should have had the energy entering from the wide end, not the side. And the second thing is they had a closed loop system, a closed chamber. As soon as the photons are reflected to be near 90 degrees, near obtuse, you need to let them out of the chamber. Otherwise, they're going to reflect at an angle that converts them to infrared, which is going to produce a momentum in the direction opposite the way you want to go. So if you produced, 1 nanonewton and then you took it away by producing 3/4 of a nanonewton in the other direction, you now have 1/4 of a nanonewton of net thrust. And that's going to be really hard to produce big numbers. So enter this thing I coined called photonic propulsion. So the first thing we ditch is tossing mass out the back for propulsion. So we're not going to use F equals ma. It's about as dramatic a change as when somebody says, I like my internal combustion engine. Damn, that Tesla plaid is fast. It's the same sort of thing. It's people are so accustomed to chemical propulsion. You know, I like my rockets to be big and noisy and explosive, and that's a rocket. Something that just shines a light. That can't be a rocket. It's kind of like when you hear the Tesla Model S plaid going down the drag strip and he just goes, yee. There's no vroom vroom sound. How can that be better? Well, this is the same sort of thing. If you concentrate the momentum transfer, you're actually transferring more momentum per square millimeter than you are by all that explosive force coming out the back. If you look at the mass tossed out the back to forward force, even the Saturn V was just barely 1.5 to 1. So when you look at all the tonnage of all the rocket, first stage, second stage, third stage, and all the fuels just to get that Apollo capsule beyond Earth orbit. That was a 1.5 to 1 ratio. So it's not 1.5 to 1 of the Apollo capsule, it's 1.5 to 1 of the entire Apollo Saturn V launch vehicle. That's why they take off so slowly. So you need to fully embrace and optimize radiation reflection pressure. Here's the things you can get rid of. Ditch the fuel tank, heating the fuel, pressurizing the fuel, cryogenics for the fuel or for the helium you use to pressurize it, plumbing for all those lines, valves to control fluids, fluid pumps, combustion chambers, exhaust nozzles, and all the required strengthening and cross members and brackets and clamps to hold all that together under such massive force. Plus all these sensors, controls, and electronics to make it all work properly and not blow itself up. So that's a dramatic reduction in spacecraft liftoff mass, parts build count, complexity, reliability, safety. There's no fuel explosions. There's no sudden cryogenic releases. Compare all that to a Saturn V. So you end up with a spacecraft size that is dramatically smaller. It costs less to make it, costs less to build it and test it. You know, initially you're not going to be launching people in them, but you might be launching CubeSats. You might have a satellite that lasts more than 10 years. But if you want to scale it up, just add more emitters and reflectors. They're small enough. And if you want to control the direction of thrust, just change the amount of energy you put into the emitters and put more emitters on it in different directions. So no more gimbaled thrusters for orbital maneuvering, and their mass and size is also gone. And if it's producing low amounts of thrust and you can direct it anywhere you want, you no longer need gyroscopes or momentum wheels. That's a big mass. So mission duration goes from 5 to 10 years to, you know, if you've got a lot of sunlight, it can go to decades. As long as the electronics last, your mission continues on, which would be a great thing for NASA and your tax dollars. It would be a bad thing for the likes of, you know, Boeing and Rockwell and people like that like to build you a new launch vehicle, build you a new satellite every so often to make their billions. So what are the additional benefits? The additional benefits are, if you've ever looked into reaction wheels, they suffer from a limitation called spin up. So if you want to rotate your spacecraft and you're using the reaction wheel in the negative direction, so if the wheel's spinning this way and you apply a magnetic force and it rotates your spacecraft, and then you apply another wheel in the opposite direction to stop the rotation, the other wheel is still spinning at the speed you gave it. How do you slow that reaction wheel down? Because the motor running the reaction wheel has a maximum RPM. As soon as you get to maximum RPM, you no longer get any effect from your reaction wheel. So you have to do something called spin down. And what you do is you use your thruster, which consumes your liquid fuel, to negate the spin of the reaction wheel, to allow the reaction wheel to go back down to its nominal spin level, so that you can then use the reaction wheel and not the fuel on a future maneuver. In the case where I found this out was in the case of the James Webb Space Telescope. They can observe for a certain amount of time while they're looking in a direction that requires the reaction wheels to spin up. At the end of that period of time, the reaction wheel is at maximum, having held the spacecraft against a force like the sun. When it's spun up to maximum, you have to stop observing. You stop observing, you consume your hydrazine rocket fuel to once again rotate it back so that it's now positioned where you want, but no longer relying upon the momentum from the reaction wheel. So that becomes an issue for the Webb Space Telescope, and that if you want to stare at something and it requires you to fight against solar wind, you can only do that for so long before you have to stop your observing, correct the reaction wheel, and then you can start observing again. If you use photonic propulsion, there is no concept of overload or spin up. You can leave the reaction going as long as you need it, as long as it produces enough force to stabilize you. As long as you have electricity, you have propulsion. And you can scale these up. Most people don't realize this, but the thrusters they use for orbital maneuvering, not for actually taking off from the ground or for going into orbit around planets, but just for orienting the spacecraft, for transferring its orbit or leaving orbit of something. Those are very, very low output reaction control thrusters, RCS thrusters. Initially, they could only produce half a Newton, and that was fine. If you go back and look at the RCS thrusters on the LEM, the Lunar Excursion Module, those were 1 and 5 Newton thrusters. So the moment that you can get to even a 1 Newton thruster, you've got an RCS thruster. And if you can do that with a much lighter spacecraft that doesn't have all the nozzles and plumbing and fuel and valves and additional sensors and electronics, and if you can make a lighter spacecraft, maybe a half a Newton would be more than enough. A 1 Newton RCS thruster would be plenty. If you can get to that level through optimization, you no longer have a need for reaction wheels, gyros for propulsion, and you no longer have a need for RCS thrusters, and that makes your spacecraft much lighter and last probably decades instead of 5 to 10 years. And another one I found out about the James Webb Space Telescope is, if you were to look at it, you would find that the thrusters are on the bottom side, not on the top side. And the reason for that is when these reaction control thrusters fire, they produce pollution. They produce noxious exhaust gases that stick to things and gunks up your science research instruments. So on the Webb, the thrusters are on the bottom side below the solar shield, so that when they have to fire, they're spitting their pollution out downward and not anywhere upward to where the sensitive instruments are. So RCS thrusters produce contamination of your instruments. If you look at the instruments on some of the deep spacecraft, the instruments that they don't want to get polluted by RCS thruster exhaust, they are on the opposite side of the thrusters, or they're out on long booms so they can be away from all the crap coming out of the thrusters. And this is even true on ion propulsion. When you spit out ions of this xenon or krypton, you don't want those coming back to your spacecraft because they're going to clog things up because they're charged. So how do you discharge the ions? You spew some non-ionized gas out. So when you're spitting out ionized atoms of xenon, just past where the exhaust is, you're spitting out unionized raw xenon gas to neutralize the charge, because if you spit the ions out, they're charged. You're flying around in a spacecraft that has a charge on it. So they're actually just going to do like a homing missile and go out and come right back and stick on your exhaust grating, and it's going to clog it up. So what they do to negate that is, as the ions are leaving, they spew some negation fuel on it, which further adds to the depletion of your fixed size fuel tank. If you're using photonic propulsion, that's no longer necessary. And people will say, yeah, but what would one of these things look like? To it, I answer, here, a picture. What you need is high flux, short wavelength, Cobb SMD LED device. You mount it on a heat sink with high dissipation, and then you put a reflector that's frustum shaped on top of it. But you want a long cone-like frustum. So you have a high base to apex, bottom to top ratio. So it looks like a cone with a very tiny hole at the front end of it. The base is only needs to be large enough to accept the size of the LED emitter. You don't need a giant thing for a little tiny LED. And the tip of it, where the otherwise obtuse reflecting photons would negate your thrust, the hole just needs to be big enough to allow the emitter wavelengths to pass through. So it can be a very, very small hole. The reflector interior needs to be as smooth and high reflectivity as possible. A dielectric mirror finish would be great, although I don't have one of those. If you have an LED that instead of all of the light coming straight out of it, it actually fans out a bit because it's meant to be a luminary for a light, then you need something to like get those photons that are coming out to the side to be more in line. And that's where this pre-reflector goes. It's just a cylinder on the base of the reflector to allow the photons coming out at an odd angle to bounce back into the mainstream, so to speak. So that's the pre-reflector cone. If you really want to optimize further, there might be some stray photons that are bouncing too much off the front edge of the cone and might want to come back towards the LED emitter. So you want to put right above the emitter a small reflector to push them back out the other end so that they don't negate the force. And of course, you need control electronics to have digital control over the propulsive force, so you can both trim the wattage going to the emitter and you can switch it on and off very quickly for the shot noise. So on the back end, you have a heat sink, and then you have the actual LED emitter, and the top of the emitter goes inside the cone, and then the light comes out of the LED and bounces at oblique angles, so you get a lot of those. And eventually, when it bounces at far enough oblique angle to almost become obtuse, you want it to go out the front. The photons transfer momentum to the reflector, and your direction of travel is the direction the light's coming out. So for those people that think we're shooting photons out the back, expecting the photons to be an F equals ma kind of thing, it's not. The photons transfer momentum, and when the photon might come out, because we're discarding it because it's obtuse reflecting, we throw those out the front. And when you throw them out the front, a photon, if you consider it as an F equals ma kind of process, the momentum is so negligible that it's not going to negate your actual thrust. So the direction of travel is where the light's coming out, which is kind of counter to why isn't it where the thrust comes out? Well, the thrust is coming out the front. The thrust is light bouncing off the inside of the reflector. So that's the direction of thrust, and it's pushing the cone forward. NASA has actually tried this with their gigawatt class lasers. They created a conical reflector, and they sit it on top of the laser, and then they fire the gigawatt laser with very short pulses, and you can actually see the cone kind of flying up in the air, and every time it gets a pulse, it goes up a little further. And then when they stop the light, it falls back down. But because it's a gigawatt laser, their conical device is probably half-inch thick aluminum that's been made reflective on the inside. But it's not a complete cone. It's more like bullet shaped, so it's rounded on the inside. So it's not a true frustum. They haven't maximized it yet. So pay more attention to maximizing the effect than juicing up the energy. So how do we calculate the effect? Yes, it is measurable as to what it should be. How have I measured it? We're going to get to that in a moment. So you have the wavelength of the photons. That's directly related to the energy per photon. You have the angle of reflection. Remember, it needs to be oblique, not obtuse. And the level of reflectivity, how reflective is your mirror? And then the flux, the photon density in photons per second. How many photons of what energy is transferring what amount of momentum per shot? When you switch it on, how much are you transferring? And then you want the power efficiency of your LED. How many watts in to how many photons out in watts per second? You want to maximize that. Now the math. This is a very standard mathematical formula. I didn't cook it up on my own. It's been known for a long period of time. Those guys that researched it, they knew all about this. So starting back as far as Maxwell, they understood this thing. So if you want to calculate the momentum in joule seconds, and we'll get to what a joule second is. A joule second is actually a Newton meters per kilogram squared. So kilogram meters per second is per second squared, sorry, is what it comes down to. And if you want to know how much weight is that in human terms, 1 Newton is about 4 ounces. So this is where you get the, how much thrust is that? Well, it's about as much thrust as it takes to lift this sheet of paper. So if you take the constant, Planck's constant, which is a very small number in joules hertz, and you divide that by the wavelength of the photons, that will tell you how much each photon is capable, theoretically, of contributing in momentum in joule seconds. That's assuming that nothing is affecting it. That's just the theoretical maximum. So you're not going to get any more out of an individual photon than one reflection with that value. But you can see that given this formula, if I'm emitting microwaves at 1,000 nanometers, I'm going to get a certain number of joule seconds out of this. But if I'm emitting royal blue photons at 440 nanometers, less than half of that, I'm going to get greater than 2 times the amount of momentum transfer per photon than with microwave. But this is an infinitesimally small force when you spread it out over a square meter. And it's only for 1 photon. But if you start ramping that up and saying, oh, my emitter can produce 10 to the 25th plus photons per second, oh, the numbers start to come up. But because if you have something that's minus 27 and you multiply it up times plus 25, it's minus 2 now. So given the quantities, even though it's a small amount, small becomes meaningful. And I'll actually show you the measurement where one of these high wattage LEDs, the number of photons per square millimeter can actually exceed the flux from the sun in the same square area. This is why damn, those tiny LEDs are bright. Yeah, because they're producing more photons than the sun. So monochromatic versus broad spectrum. Why would I want a single color LED when I can get one of those white LEDs and produce more light? Remember, it's not the specifically total amount of light coming out. It's what kind of light is coming out, what wavelengths. And if you were to get yourself even an ultra bright white light LED, a 15,000 Kelvin LED, it's producing a lot of its light in infrared, in yellow, and in green, as well as low end blue, not near UV blue. So it's producing a large number of photons that are much lower energy level. So I'd rather have a higher frequency, a much shorter wavelength monochromatic LED that I can pulse with very short pulses. And I can get those in 5 watt instead of 3 watt or 1 watt. I worked in 3 watt just because everything's cheaper. So a royal blue will emit at 440 nanometers. I just recently found out you can get violet, which is borderline, even more borderline UV at 395 nanometers. But the difference between 440 and 395, it's not, unless you're going to be making something big, it's not worth getting that close to UV. You don't want it to be a visual impairment kind of thing. So I want a monochromatic, high output LED. Royal blue is great. I want to make my reflector as reflective as possible. I want to make my shape of my reflector good for getting lots of multiple reflections out of it. But if I want the closing on 90%, I can get that with a front surface instead of a electroplated. But if I want 99.9+%, it needs to be electroplated, and I don't have one of those at the moment. So here's how angle of reflection affects the amount of momentum transferred. So this works at any wavelength. If you take a photon and you bounce it off of a reflector at a certain angle, you reduce the amount of momentum possible to be transferred by the cosine squared of that angle. So if I said, I'm bouncing my photons off at 15 degrees, very shallow angle, I can get 0.933% of the original momentum that photon should have produced. So I'm getting a lot of it by having a shallow angle. You can see that as the angle increases up to 90 degrees, less and less of my potential momentum is transferable. And when I get to 90, it actually goes to 0 because the photon gets absorbed and transferred into infrared, which now comes out at the opposite direction to the way it went in, which is a force in the negative direction. So I don't want my photons reflecting at 90 degrees. So I don't want the end capped. I want the end open. Let those photons go. Can't use them anymore. But if I have a nice long conical shape, I might get a photon to bounce several times. And it's not like the photon gets depleted when it reflects. If it gets absorbed, that's different. But if it just reflects, it doesn't really get depleted. So you can have a couple of bounces. So how does reflectivity affect the end result? Directly, by a percentage. So if your surface is only 85% or 0.85 reflective, well, whatever you thought you just got out of those photons at that reflection angle, you're only going to get 85% of that if your surface of your reflector is 85% reflective. That's what Maxwell had to work with in the early 1800s. Silvered coating gets you to 98%. But those didn't come about until 1835 after Maxwell was done. But contemporary dielectrically coated mirrors, which get you to 99.99% reflectivity, those were invented in 1937 after Nichols, Hull, Bell, and Green already did all their work. So they were working with just silvered front surface mirrors. So they were at maybe 99%, but not 99.99%. I've been working with something that's around 98, 99%. It's just a polished front surface reflector. Okay, flux density. Here we go with more of the math. I described the amount of momentum you can transfer with a single photon out of an LED. But LEDs don't produce a single photon. They produce lots of photons. How many? It varies by the LED. You have to actually get the specs from the manufacturer. So the LED I'm using is circular. It's 7.3 millimeters in diameter, thus has a square meter area of, it's less than a square meter by a lot, 4.1 times 10 to the minus 5 square meters. So if you want to say, how much is it producing, and then blow that up to square meters, you're going to get a very small number. But you're not producing it over square meters, you're producing it over to square millimeters, because it's a very small area, and all of the light coming out goes into your reflector. So the radiant flux of sunlight at noon on the Earth is 1.321 times 10 to the third watts per square meter. 1.3 kilowatts per square meter. But that's over a square meter. Now, if you divide that down over the same surface area as the LED, then you're going to see that that's a much smaller amount of light that the sun is producing versus the LED. And if you get yourself a 5 watt or a 10 watt LED, you're producing far more photons over that small area than the sun would produce. So lots of photons. So if you have short energy pulses that are 100% aligned, that would be great, but let's assume that you've got a 50% duty cycle. So divide, multiply it again times 0.5 and reduce it some more. So all I've done so far is go, look at this incredibly tiny number you can get per photon. But look at how many photons there are. And if you sum it all up, and then you start dividing it out by what's your reflectivity, what's your reflection angle, what's your reflectivity of your surface, what's your flux, what's your shot noise, it just keeps trimming it away more and more and more. So you would think it'd be a really small number, but these LEDs produce so many photons. It's a larger number than you think, but it's still small. And then there's power efficiency. How many watts in versus how many watts versus watts of photons out. So a 3 watt, 440 nanometer LED, you put 3 watts in, you get 1.4 watts worth of photons out. And if you know what that number is in watts, you can now calculate by the wavelength how many photons are coming out of the LED per second. But then you have to calculate your 50% shot noise and the angle of reflection, and then the reflectivity of your mirror, and keep docking it all. So let's calculate an end result. So we start with our LED, we determine the flux of it, we calculate that, let's say 20% of those photons are just going to shoot out the center. You do have that little hole at the front. And then you calculate the angles of reflection and say, well, if it's 15, 30, or 60 degrees, those are going to be meaningful. As soon as it gets to 90 degrees, out the front. So you don't even count those. Presume we're at least at 85% polished surface. I'll show you why it's only 85%. Presume that you're going to have a shot noise problem, so only 50% of that is going to be usable. And then you convert your joule seconds to newtons per second, and you get 5.859 times 10 to the minus 5 meters squared. You map that into newtons, and you get 1.099 times 10 to the minus 4th. So that's a small number. But take a look at the actual number. It's 109 millinewtons, not micronewtons, millinewtons. And if you remember what the NASA N-Star engine of the Dawn space probe produced, it produced 14 micronewtons. So this is a lot more propulsive force than the Dawn spacecraft in a very lot smaller space, simpler, less complicated, less plumbing, no fixed fuel supply. So this is something worth looking at. And if these garden variety commercial LEDs are good for 5 years of continuous output, so long as they have a heat sink, then if you trim that back a bit to reduce the heat noise and say, how about if we only wanted 50 millinewtons? Well, 50 millinewtons is still more than Dawn produced, but that might extend your 5-year lifespan to a 10-year lifespan or longer. But there's not been any dedicated research into maximizing any of this stuff. This is just taking the raw data and then discounting it heavily. So these are very conservative numbers. So how do we optimize it beyond that? Well, we could say go to violet and go to high wattage, or we could say, this is for deep space. We don't care if we emit in deep UV and really go wild on it. We could go up to, 3 watt or 5 watt or 10 watt, or you can buy 100 watt LEDs right now today. They're bright white output, they're not royal blue, but you can certainly maximize the wattage. And over time, the watts in to the watts out, the manufacturers of these LEDs are just going to continue to improve that on their own. You won't have any need for NASA rocket propulsion. They'll just do that because that allows them to produce more efficient LEDs, so less power out. Therefore, all the light bulbs in your house consume not 8 watts, but 4 watts. So that's why they're going to do that. And you want to use fancy electronics to do femtosecond switching at high rates to further do the photon phase alignment to reduce the issue of shot noise. That would improve things. And then make your reflector even longer, even more oblique reflections. And, the reflector can be custom made and not anywhere larger than the LED aperture itself. And you can make LEDs that all the light comes out the front instead of fanning out as a light bulb. And you can make the reflector uniformly smooth. I found out that you can actually take a mirrored surface beyond what dielectric coating can do. And that's if you use helium ions to literally grind away the surface of an aluminum surface to make it reflective down to the wavelength of the light you're shining on it. So if they want to create a purpose-built reflector for this to eke out another few percentages of reflectivity, that's technically possible today. They just have to want to do it. And the egress hole at the apex should be as small as possible. Yes, but have you built one of these things? Yes, I have built one of these things, and here it is. So this is a 440 nanometer 3 watt LED. The LED is soldered onto a little tiny printed circuit board that's kind of petal shaped like a little flower. It's surface mount, so it seats right to the top of the circuit board. And I use heat sink grease between the LED and the circuit board to transfer heat into the circuit board. The circuit board actually has aluminum on the bottom side of it to transfer more heat. I then put more heat sink grease on the bottom of the circuit board, and I then mount a copper heat sink that uses pin fins, which are the most transmissive for heat sinks, to the bottom of it. So the LED produces the light, the heat from the LED, that difference between 1.4 watts and 3 watts, goes into the heat sink and radiates randomly out the back. There's no fan or anything. It's not going to produce a propulsion out the back. The cone is actually a stainless steel seamless pastry tip that you use for putting gel icing for very fine print on birthday cakes. So if you've ever seen a birthday cake with lettering on it that is sort of faint colors like blues and greens and reds, and almost looks clear. And it's kind of this jelly looking stuff. Well, that's what you squirt out. And you squirt it out of a nozzle that has 1/10 of a millimeter diameter, which is enormous compared to the 440 nanometer wavelength of the royal blue light. So that's the cone. I shined it up on the inside, so it's a front surface mirror. I'm guessing I'm getting at least 85% reflectivity.
How did you shine it?
How do I shine it?
Yeah.
I have a Dremel tool with a shining brush that's cone shaped, and I run it inside there to get the reflectivity up all the way to the tip. So I make it as reflective as possible. You can see the reflectivity of the outside of the stainless steel. The inside is much shinier than that. The power source, well, given that it's a 3-watt LED, that's easy. I use a 1S lithium polymer battery like you'd use in a little quad rotor, little helicopter. To keep the connector weight down, I use a 2-pin nylon JST connector, female to male. The heaviest part of the wiring is actually the tape. Now, why am I using tape to hold the wires together? Because solder is heavy. The tape is much lighter weight than the solder. So the wires are just twisted together and then taped together with plastic tape. But I didn't solder in the battery because I want to play with it. When the battery drains down, I disconnect the battery, connect it to the charger, charge up the battery, and then I can use it again. Now, obviously, I don't have a maximum reflection on the interior of the cone, and I do not have it completely over the sort of 60-degree off angle photons coming out of the LED, which is why you see that bright blazing glare of light coming out the bottom side. If I could get the cone to be down further over the printed circuit board to more cover the LED, I would, but then I would have to customize the cone or customize the printed circuit board, and I just wanted a proof of concept. But you can see how deep blue the light is coming out of that, but it's so many watts of deep blue, so bright that my phone camera saw it as white. It's not actually white, it's very narrow band at 440 nanometers, but the energy level is so high, the camera said, oh, that's way off the top of the receivers, the photons in the camera, and we know that's white, so it just made it white. But if you look to the right side, you'll notice that there's a blue cloud of light coming out there. That's the diffraction of the spent photons that I'm letting out the front end. If you had to say, which way does this thing travel if it was in space? It would travel from left to right, or from the low numbers on the ruler to the high numbers. But there's light coming out the front. How does that work? It's not F equals ma, folks. Now, all of these parts are readily available on Amazon. You can go buy them today. There's some assembly required, a little bit of soldering and taping, glue, some CA glue to glue things together. But it does this. So the next step would be, and how do I measure this thing in a vacuum? NASA's not offering up their fancy gear, so I have my own test chamber that I built. I bought a 5-gallon glass top vacuum chamber, and it came with, I bought it as a package deal. It came with the chamber, the lid, a silicone seal, the plumbing, the valve, the filter, and the 2-stage 7-gallon per minute vacuum pump. This sucker will suck it down to 29.9 inches, which is as close as I'm going to get to a good vacuum. And it'll keep it in the chamber after I switch off the pump for 24 hours. So it's a good silicone seal. It's a spun aluminum chamber with all the valves and plumbing assemblies all have Teflon PTFE sealant on them. So it holds the vacuum very nicely. Okay, so I've got my propulsion source, I've got my vacuum chamber, but now I need to have something that operates inside the vacuum chamber that will measure something on the order of, millions of a Newton force. I don't have one of those. That's the stumbling block. So you can find the parts to make the emitter. You can find the parts to make the reflector. You can find the parts to make the vacuum chamber. It's simple enough to fabricate. You can do it in your home lab, soldering a little CA cement, you're there. Stumbling block is getting the nanonewton force digital recording scale, because you want to reliably do this multiple times to get to your 5 nines. Turns out the NASA Glenn Research Center in Ohio, outside of Cleveland, actually has a nanonewton impulse platform thrust stand. And if you remember back to the picture where you saw the EMDrive sitting in this big chamber on rails, that was it. That was the nanonewton impulse pendulum thrust stand. They have one of these. So if I could build a poor man's version of that and just measure, is the result 0 or non-zero? It doesn't have to be huge. It just has to be repeatedly non-zero of a sufficiently large number to discount it against any infrared heating of cables, the downside of the EMDrive. Turns out the Glenn Research Center has actually produced a testing manual on how to do this. And they've actually tested it using semiconductor lasers. I wonder how they were doing that. If NASA was actually using semiconductor lasers to measure nanonewton levels of thrust in their test chamber, couldn't they connect the dots and go, hey, this has some merit. Let's research this. Nope, they haven't done it. I'd like to have access to one of those scales. I'll see if I can't build myself one. But unfortunately, right now, any peer review prospects for this are still too amused with themselves over the joke of the impossible drive, and they're blinded by the false promise of the EMDrive to take any of this seriously. If you look at the history of ion propulsion, from the point when ion propulsion was first proposed until they actually put it on the Deep Space One spacecraft to prove it out as a demonstrator, was 40 years. So 40 years went by while NASA knew about the physics of ion propulsion before they ever had the faith in it to actually make a propulsion device and put it on a deep spacecraft. 40 years. So hopefully this won't be another 40 years, because after all, there's a huge head start in proving the concept. James Clerk Maxwell in the 1800s. But now we have is much better everything to make it much more efficient. So here's the 3 kinds of thrust measuring stands, as they call them. Here's how you do it with the forces. This is not the mechanics of it. This is the physics of it. And the torsion balance, as they've often called them, is that one on the left, where you put the propulsion source, that's your M, that's your mass. You put that out on the end of a lever arm, and you make the lever arm as big as you can. And you know where your starting point is, that's your 0 point. And then you have that connected to a central balanced vertical wire. And you have a piece of wire that changes either voltage or resistance based upon it being torqued. That's that coil spring looking thing. And then when you switch your force on, it wants to rotate it using very small amounts of force. But the difference at the theta angle between Y, where you started, and where it gets to is the force F over time. So the force over time gives you your newtons. So if you can build one of these things and it works in a vacuum, and the electronics necessary for recording the net thrust also works in a vacuum, that's it. But that's going to take some brainstorming, which I haven't got time for at the moment, which is why this is sort of sat in neutral for years after I came up with this.
By the way, this is a model based on the discovery of gravity. Like the first measurements of gravity, like two masses, they did rotation torque
Right.
like this too.
Right, which is why the one on the left is actually dated back to the 1800s when they were initially measuring the force of gravity. The two on the right are more contemporary. I think the one that you saw the EMDrive on is the third one. That's kind of like the moving rail. So it rotates. One of the reasons why ion propulsion took 40 years to actually be put onto a spacecraft is something called implausibility. If you're so used to big, powerful things, how can something that produces such a small amount of thrust ever be usable? It's a joke. It's implausible. So ion propulsion was implausible for 40 years. The EMDrive is, as it's currently perceived, is inefficient and has some counterintuitive problems. So it's just as implausible. And the moment that you bring out conservation of momentum, if you don't have the scale to measure it, and if you don't produce something that is above 5 nines, that will be your downfall. Is it doesn't obey the conservation of momentum. Well, actually, reflection transfers momentum. It conserves the momentum. Think about it for a moment. You have an electron associated with the nucleus of an atom. You apply energy, and the electron wants to move to a different shell of the atom. That's because it's taken in the energy. Well, the atom doesn't go anywhere. It doesn't recoil. Where's your conservation of momentum? The conservation is the electron moves out. So that's how you conserve it. Well, the same thing is true on the way back in. So if you have an electron that's been excited and it's on an outer shell and it gives up a photon, but when it gives up a photon, the atom doesn't move. Oh, the electron moves inward. There's your conservation of momentum. So when the photon leaves the atom, it's carrying momentum. How much momentum? Well, a photon at rest, whatever that is, because if a photon's at rest, wouldn't it be inside of an electron? If a photon is at rest, it has zero mass. If a photon is moving, well, we know that it has momentum, and the momentum is related to its wavelength.
Basically, what you say is energy.
Yes. So when that encounters a reflective surface, it reflects off of it. And when it reflects off of it, it transfers a portion of that momentum into the surface. Well, if you get enough of that, you're moving the surface. Now, where's your conservation of momentum? It was already conserved when the photon left the atom. What you're having now is a transfer of momentum into the reflector, but it's not, you're not, if it's in 90 degrees, you completely absorb the photon, and that's how you conserve the momentum. But if you do it at an oblique angle, you're transferring momentum. That's your conservation. And if it didn't work, if a photon really couldn't move anything, then there wouldn't be a Nobel Prize for microscopic tweezers. And the other thing they found out is gravity wave measurements make use of lasers. When they upgraded the lasers to be 60 watt and they first turned on the lasers, the mirror moved. They have mirrors at each end of the 4 mile long tunnels. Now the mirror didn't, oscillate back and forth. The mirror moved sufficient to make them think they detected gravity waves. Because remember, the way that the Michelson interferometer works is you have light going down 2 tubes of equal length and then coming back to a light joiner after it goes through a beam splitter. But when it comes back together, if either path is longer than you started with, it's going to cause a differentiation, which means light is going to be produced onto the receptor at the opposite side of the junction. So the mirror moved, obviously, because they detected light, which they thought was a gravity wave. And then after they turned the lasers off and let the mirrors debounce, let them idle down, then turn the laser back on. Oh, they got another detection. And they rationalize that the mirrors are moving microscopically, but given that it's a 60-watt laser being concentrated into a concave reflector, that's a lot of flux. And those lasers are not ultraviolet, they're infrared. So they're very low energy laser beams. If this was implausible, then there wouldn't be a Nobel Prize in it, and they wouldn't have detected it at the gravity wave detectors. So it exists, it's a thing, optimize it, see what you can use it for. So if it's such a small amount of Newton's force, how would it ever be usable to launch something from the ground? Turns out it's the same way that we launch a Saturn V, just on a very much smaller scale. So a Saturn V, when it launches, the first stage burns through its fuel in a matter of well under a minute, and then it gets jettisoned. Well, if you could get a very high voltage source with a lot of emitters, and you mounted that beneath a smaller emitter that was physically not connected, you could make a concentric ring pusher. So you could have no batteries, very small wires going to your ring of very bright LEDs. And these can be, 500 watt scale if you wanted them to be. And they would provide the initial kick. But as you got to the end of the wire, that ring would fall away and you would have momentum applied to your upper stages where you dropped off the booster. Now, if you think that's not a thing in physics, have you ever dropped a small super ball on top of a large super ball? The force from the one at the bottom pushes up into the smaller one at the top and causes it to rocket away, and the bigger super ball only goes up a few inches and then drops to the ground. It's the same thing. You have an energy transfer pusher. That would be your first stage. Your second stage might be a lot fewer emitters and might have a small battery in it. It'd be good for only a few seconds, but it would also be a pusher. But since it's lower mass and producing high output, it would be another pusher. So your second stage would push until it ran out of battery power, and then it would just fall away. And now you've transferred your first stage and your second stage momentum into your final stage, which is very small, has an emitter, and maybe a solar cell on it. But the solar cell would be on the outside of your reflector. So it would indeed be very small. So that's how you get something that would be the size of a thimble to go into Earth orbit, is stages. Now, you're not going to launch something the size of an Apollo capsule this way. Maybe in the future, once you optimize the hell out of all this technology, but not in the foreseeable future. And if you think that's not the way things are done, you might want to look at a guy named Goddard and his first attempts at launching things. The first time he wanted to launch something, if you've ever heard the phrase, it goes over like a lead balloon. His first attempt at launching something was a lead balloon filled with helium.
How did it go over?
Like a lead balloon. But he thought he was going to produce this thing that wouldn't leak out the helium, and the helium would loft it. Turns out helium's light, but lead is heavy. But nowadays we launch telescopes that weigh tons using helium-filled balloons, and they use mylar. So we use high-tech materials in the balloon. We make the instruments as light as possible using aluminum and electronics, and we give it just huge amounts of helium, and it goes up to about 100,000 feet, and then the balloon pops and it comes back down by parachute. What if we did the same thing? What if we created very small spacecraft that we could get up to, let's say, I don't know, the mesosphere, and now it could be using its very lightweight mass, very low propulsion, to keep itself aligned in orbit in the mesosphere, and it could do sampling. You could have a couple of very simple instruments on it. There's stuff to be done. And when you want to compare it to other things, if you've ever seen one of those Crookes radiometers, that's that clear glass light bulb looking things with the black and white veins that spin when the light is applied to it. that bulb is not a vacuum. You actually have to have a slight air pressure in there because it actually works off of infrared heat transference. That's why one side of the vein is black and the other side of the vein is white. I've got one of those myself, and when I shine my 1 watt blue laser on it, boy, does that go fast.
Well, when we make all the Crookes radiometers move at the same time in a museum, me and you, we
Yeah,
have like a wall of radiometers. We make all of them move at the same time
yes,
until they call us attention.
but that's not photonic propulsion. It's just transfer of the light into infrared, and the infrared heats the gas, and the gas provides an expansion force which rotates it. And yes,
No,
you
that
can
was not photonic propulsion. That was us misbehaving museums.
no, that's what I'm saying is a Crookes radiometer is not photonic propulsion. It's just you take the light, you absorb it into the black vein, it converts it into infrared, the heat heats up the gas inside the bulb, which causes the bulb to receive a pushing force from the expansion of the gas. So yes, photonic propulsion is not a Crookes radiometer. It's not the same as a ion propulsion or a Hall effect propulsion or the nuclear version, which is a Vasmir drive or a nuclear photon rocket. These are all F equals ma based propulsion, nothing fancy there. It's not solar electric propulsion. This is just another way of saying it's an ion or Hall effect thruster, and we use solar panels to generate the electricity. That's still F equals ma. It's not quite a solar sail either, because this doesn't require gigawatt lasers on Earth. The reflection angle is oblique, not obtuse. And you do know that sails can't tack in space. So how do you slow down once you get to wherever you're going? You hope there's a star nearby that you can flip your sail the other way around and slow down over a long period of time. And the amount of force you can get on your sail declines with distance. So the farther you get away from your sun or your gigawatt lasers, the less force you have access to. But if you take the energy with you in the form of a photovoltaic cells or RTG, you're taking the energy with you, so you don't have to worry about distance. No, photonic propulsion is not a warp drive. Those are still decades away. And by the way, they came to this conclusion recently. If you create a warp drive around your vessel, it doesn't go anywhere. You still have to have something that will move your vessel within the warp field. So you still need F equals ma propulsion on your warp drive, which is why when you see the Enterprise flying off at warp speed, its impulse engines are also glowing, because that's how it moves within its warp field. And you might have also heard about a Fern-Woodward Mach effect Casimir or Mega drive. This is not actually a Star Trek impulse drive, although they're comparing it to that. And it's not ion propulsion. This is literally a piezoelectric effect where you shoot energy into a crystal and the crystal oscillates. And when the crystal oscillates, there's a presumption it'll create a differential acceleration, and that will move whatever the crystal is attached to. But as of yet, they've had no peer review confirming that that exists. I think that's sort of in the same category as the EMDrive, and that if you attach the crystal to what you want to move physically, and then you expect the crystal to expand and contract, it's going to stabilize the expansion and contraction because
Yeah,
you have it physically
both
attached to
ways.
something.
Yeah.
You physically have it attached to something. So yes, it will oscillate, but will it move the thing that you have it connected to? No, it counters itself in place. So, but Dr. Fern really believes in this as the next form of advanced propulsion, but he has yet to produce a result in the 5 nines peer-reviewed category. So genuine photonic propulsion is different. It counts on radiation reflection pressure and optimizing the momentum transfer through the use of emitters and reflectors.
I have a question.
Yes, go ahead.
At the beginning, you were talking a lot about mirrors and how they have improved over the ages.
Yes.
my question has to do with the mirrors and what, you know, when you look at a mirror, I mean, there are mirrors all over the place in your house. And I guess if, you know, I would have thought if somebody asked me why we improved mirrors was because people wanted to look at themselves better. But I'm
Exactly.
thinking that may not be the reason why. Maybe,
Oh, that is.
oh, it is? Okay.
Yes,
So
the
I think in these
first,
scientific needs.
no, the first mirrors were for the purpose of looking at yourself to make sure that you appeared well in public. And so the first mirrors were nothing more than polished metal. You know, they found that when you shine up your sword really good, you can see yourself in your sword.
Yeah.
How about taking a round piece of metal and shining it up so I can use it to see if my face is good, if I've got my makeup on straight. Not women, because back in the day, men even wore makeup. So you'll find in ancient Greece and ancient Egypt, mirrors made from polished metal. And those are good for about 85% reflectivity. But they're also heavy and they're hard to produce. And when they came up with silver coating the backside of clear glass as a means of creating a mirror, oh, well, that will get you close to 90%. Okay. Well, people don't care about that stuff. But now if you want to use it in a physics experiment and you want to bounce a beam of laser light, you want to not lose anything in the mirror. So you want a front surface mirror so you don't get any funny reflections. If you ever look closely at a mirror, you'll find you actually get two reflections off of it. You get one reflection off the back side and one reflection off the front side, which is very much dimmer, but you can see them in bright light. Well, in physics, in optical instruments, you don't want that second reflection. So what you create is a front surface mirror. The light doesn't go through glass. It's a coating on the front of the glass that is reflective, usually aluminized, copperized, or gold coated, and that's what gets you reflections. The mirrors on the James Webb are beryllium alloy, and that's so that they reflect specifically in the infrared spectra that they're doing their observing. So if you're a scientist and when you want a highly reflective mirror for your physics experiment in optics, then you want obviously one of these dielectric coated mirrors. And if you put the mirror in a chamber with an inert gas like argon, and then you take a chunk of silver or aluminum and you vaporize it with a high voltage, then the ions of that metal will deposit on the glass surface and you'll create a dielectric coating, and that is 99.99% reflectivity.
You also have to have a pretty flat piece of glass.
Yes, your glass has to be uniformly flat, which is why they found that if you want to make a really flat surface, you take helium ions and you blast away at the surface of a piece of aluminum oxide, and you can get a surface that is accurately flat to within 10 billionths of a meter, 10 nanometers. And then when you apply your coating, you get a really good mirror, and that's 99.99999% reflective. That's where you get your 5 nines reflectivity. So it is possible that they're not cheap because it takes a lot of stuff, a lot of equipment to do that. But dielectrically coated mirrors that are 99.99% reflective, those are easy to come by. Look in your Orion telescope accessories catalog. You buy one of those diagonal mirrors and you see it's 99.99% reflective, which is great. It's dielectrically coated, so they're cheap. So if you dielectrically coat the inside of one of these pastry gel cones, you can get it high enough in reflectivity to change it from whatever number of millinewtons it is to maybe 1 or 2 more millinewtons just by improving the reflectivity. So the Achilles heel of all chemical propulsion, even ion, is it's fixed at launch fuel capacity. When the fuel is gone, you're at end of mission. The physics of radiation reflective pressure is sound and field proven. The EM drive is a form of photonic propulsion, although it's very non-optimal and actually has a couple of barriers to making it function more effectively. The goal should be for fully optimized photonic propulsion designs. And if you want to launch it from the ground, should you ever get wacky enough to try that, use multiple stages and start with the first one being very high output and powered by a source on the ground, so that your launch weight does not include batteries or solar panels for that first stage. It's just a couple of lightweight, long copper wires. And if you think copper wires are going to drag it back, there are shoulder-launched missiles that the US military uses that are wire guided. They have a giant spool of wire on the back of the missile, and it plays out over miles. So, yeah.
Yeah,
you can do that.
submarines have them too.
Yeah, you can do that. If you want it to be accurate and you don't want the bad guys to commandeer it or affect it, and you want it to be automatic right until it hits the target, you wire guide it. So an individual emitter reflector assembly would be dramatically smaller than EM drive, and if done properly, would produce far greater propulsive force, likely on par or better than a current ion propulsion unit. But the mass is less, the size is less, operational duration is much longer. And we're not talking about light speed, but if you run it over a multiple year period, it'll be significantly faster than any F equals MA solution you have today.
Very
So
nice.
any questions?
What is CA glue?
Oh, cyanoacrylic, super glue.
Yeah.
Yeah, it's
Okay.
cyanoacrylic. And you can get it in varying strengths
Yeah.
and in varying amounts. The way I buy it is I buy it in a 12 pack of these little guys.
Yeah.
And the reason why I buy small ones in a 12 pack is no matter how tightly you cap it, after you've let it get exposed to air, come back a week later, it's going to be solid.
Yeah.
So if you get it in small amounts, they even make them half this size, which would be great if I could buy them in 12 packs, but I can't. And I buy the original formula super glue, which is very runny, but it's also something that solidifies in under 60 seconds. And yeah, it'll catch your skin if you're not careful.
Yeah.
Even when you're careful, it catches your skin. There is no salvation.
Well, it comes,
I agree.
no, it has a very low surface tension, and it just crawls over flat surfaces. So if you put your finger an inch away from where you put the drop, and you actually let like 2 or 3 drops out, it'll go flat over that surface very quickly and be underneath your finger before you ever realize it.
Yes, by the way, it evaporates very easily. And when we did shoestring digital printing,
Yeah.
so like when I was in the army, we did those techniques for investigation. So we open one of those, put in a little dish, and then let the vapor so it fixes the digital prints. It's like you dust, and then you put in a closed bucket with a lid of acrylic glue, and then it fixates the
You'll often see that on crime story movies and TV.
Oh, yeah.
Where we need to get the fingerprint out. Oh,
Yeah.
I'm the
they have
genius. I'll just put it in the
aquariums,
little
they have
chamber with some
specific-
CA glue. Yeah.
Yeah, but ours was a bucket or old like aquarium. It's like all shoestring, and then we cook with
I'm assuming that the FBI spends a good portion of your tax dollars to get the professional version.
Yes. No, ours was shoestring. It's mostly just to learn the technique.
Well, everything I do is on a shoestring. I like to call
Yeah.
it dirt cheap because that gives you the idea. Shoestring might cost a little. No, dirt cheap is like, how low can you go?
Can I explain a little bit of the forces of in the incidence angles? You were explaining, I actually draw some stuff.
Okay. You want to
So-
share?
Yes, I don't
Okay,
know
I
if I
will
can
stop
check in my
sharing.
phone. I don't know if I can check. My settings, disconnect filters. I don't think I can share because
Oh.
I'm on a phone.
Have you got a hyperlink that you can put in the chat and I can share it?
No, it's because I draw on a paper.
Oh,
Unless you make
We can see
biggie.
that. We can see that.
Oh, you can
Yeah,
see
hold
hold it
that.
up to the
Okay.
camera.
All right. So starting from this, that's very simple.
Mhm.
You can see here that whatever angle you hit the surface, the force comes out in a perpendicular to the
Yes.
to the force.
Yes.
So that's the basic understanding how the trustums work.
Yep.
So it doesn't matter which angle. So can you see the small angle and then the longer angle? As you can see, all the forces of all the points that hits the surface, the force is perpendicular. So thinking about that, as you go and look at the cones, so you can see here that this is a more closed cone and this is more open cone. This would have more forces because the angle is open. But then you would lose a lot of energy because this is open, and then where is going to be your emitter?
Yes.
And
You have to optimize the ratio of the angle of incidence, the height of the cone, and the openness of the hole at the front end.
Yes.
You want the force to go forward.
Even if the emitter was like the full size of the opening,
Mhm.
you only have like very short reflections because
Yes.
this is a smaller surface. So you have like here one time, and you out to the
Yes.
other side. So
That's why it has to be really long.
even though that is more force because the angle is towards to the direction that's going to move. So it's force. It's bigger, you have less reflection, so you get a little bit, so you have a ratio of you have more force, but you have less reflection.
Right.
Over here, when you have this, the angle is more open, so you have this, so the force is smaller. But then you have more reflections because you can have a smaller weight, and then this, can you see more little arrows that you see here? Is reflecting more and more and more. So that's why you have to equilibrate the angle of incidence, and also because you have to choose your battles. But then here is like a little explanation of the forces. So as you can see, I translate what you see here for force here and force here. I connect that force, and then I'm calculating the resultant force that goes to the motion. So imagine that in here you have that force that's connected that goes that way, a force that goes that way. So the resultant force is this one. Now, if you have a little bit more, the angle it's closer to perpendicular. Over here, when you see the angle going more that way, so it would be a smaller cone, a longer cone, it would have a force that would be very small. So you can see the arrow here is very tiny in comparison. But then you have more of those forces because that photon is reflecting all over the place. So then you choose your battles. Now, I don't know if that helped for you to understand a little bit more how the thing works. But I still have trouble.
I understood that, which is why I described the EMDrive as being stubby, squat. It needs to be much longer. It needs to be a much taller cone, because think of it this way. How much does a penny weigh? Oh, it's a trivial amount of weight. How much does a million pennies weigh? Oh, that's massive. Same sort of thing. How much momentum can I transfer with a single photon reflecting at an oblique angle? Not much. But if I can make a lot of them do that and make them do that multiple times, the summation is large. So that's the idea of using a very long cone that's reflective on the inside and make it not much bigger in diameter than the LED emitter itself. But, it's all implausible until there is a digital peer-reviewed number.
Yes, but then I'm still having a little problem with it, is that whenever you transfer momentum, the emitter of your photons is in a fixed position. And whatever you're pushing away, you're pushing with the photons. That's kind of my understanding. I'm still having problems to understand the principle. I actually read the papers that you sent to me, but I couldn't understand how a emitter could be on the spacecraft and making the spacecraft move. That's the barrier that I have in my mind that I haven't understand yet, the physics of it.
It's fixation on conservation of momentum. The momentum that is transferred.
No, not the conservation of momentum. It's the transference of momentum, because you got to understand that the formula of momentum has mass and a force.
Yeah. So
as my problem is to understand how something that's moving together is transferring momentum. Unless if that thing that's moving together with the spacecraft is losing mass. If doesn't stay static, it's moving together with, then it should be losing mass.
that's an F equals ma response. And if you're losing mass, and the mass happens to be the photons going out the front, you're losing a very tiny amount of mass.
No, it could be the material that makes the power source. Imagine like you're transferring, you're doing fission. You're moving, you're separating an atom, breaking a smaller part, and then energy comes out. So that mass, like the uranium, the large uranium, when it fisses, it loses energy. That even if when you get like the resultant atoms together, those two together are lighter than the original, because then it lost mass that became energy. So in that case, maybe the battery is losing energy if the whatever is powering that light that's moving needs to be losing mass in form of energy.
So if I hear what you're saying, that means that when I drive my electric vehicle and I go from 100% full battery charge to 25% battery charge, my vehicle should be lighter, right?
Yes, yes.
Have you ever measured one?
No, but batteries do get lighter.
Really? By how
Yes.
much? By how much?
Very little, because you're talking about here loss of energy. So you're losing electrons, or you're losing photons. So the mass is very little, but they do lose weight.
But
So
you're not ionizing the atoms. This is not ion propulsion.
So you imagine that I have two molecules of hydrogen, hydrogen 2, and then I make into a molecule of helium. So you have helium 4. So I have 2 hydrogens and I have 1 helium. They have the same mass number. But if you measure in mass, a real mass of 1 atom of helium and 2 atoms of hydrogen, hydrogen is heavier. 2 atoms of hydrogen is heavier than 1 atom of helium.
Yes.
Because some of that mass that used to go into the nucleus to add more force, that became photon in energy. So that lost energy. So the only way that I can understand photonic propulsion is somehow whatever is emitting the power is staying static somewhere, or is losing mass as it goes together.
And I think if it was chemical propulsion, that would make sense.
No, I'm just explaining to you in form of physics. When photons mass was transforming to energy in the form of photons. When you fuse,
you're not transforming mass into photons.
Yes.
You are not transforming mass into photons. What you're doing is you're charging up electrons and making them emit a photon. The atom stays intact, and it's not even ionized.
But what is producing energy in your spacecraft in that case?
Photovoltaic panels or RTGs. It's not nuclear fusion.
So then as photovoltaics, yeah, in that case of photovoltaics, because you use the sun to charge the batteries to move the photon.
Yep.
Huh, that I can't understand. I don't think that would cause motion. Maybe if you have a RTG, you would have motion. I'm still not understanding how, because
It's
if
not
you have
it's
place
not
where-
radioactive decay. It is absolutely not destroying atoms at all. It's not even ionizing.
no, you can lose energy. So let's just think about when you get to, you add energy in the system, doesn't matter. It could be even chemical
Yep.
or electrical or
Yep.
whatever it is.
You're
When you
taking the
have
light,
something
you're taking the
strong,
light and you're applying it to the atoms to make it emit photons.
whenever you have electrons have mass. So if you collect electrons,
Yep.
they have mass.
Yep.
And they make it the stuff heavier. So if
Mhm.
that electron is used up to produce photons, you're gonna lose mass.
But the atoms already exist in the dielectric, in the battery. The atoms already exist in the
Sure,
photovoltaic
but they are
cell.
charged and then
Right.
you can move and
They don't
continue.
get
your good.
they don't get ionized, they get charged and they emit photons.
Yes, so they get heavier as they get charged by the sun, and then they emit photons and they get lighter. Maybe that's the way.
Well,
I still don't understand that, because
that would-
like this is very difficult for me to understand, because I've read some physics, I know a little bit, but I still don't understand, because I know you can move stuff with light, because whatever is producing the light is static and the light's moving. But when you're moving together, the emitter with the whatever it needs to be moved, that's when my understand fails. And
Okay.
I explained to you that before, as I still, it's above my pay grade.
There are those times when I believe that science has a dogmatic attribute. People get involved in it and they think, well, this is the way we've always done it. This is the way it can only work. And therefore anything else is just, no, I don't want to hear it.
No, it's not that, no, I don't want to hear it. I just don't understand.
That's fine.
Isn't it,
And
though,
I'm not,
can I make a
But
statement?
not understanding does not insert
Yeah.
doubt.
no,
Okay,
Can I make a statement?
certainly.
sure.
Okay, you went over the impossible statement in
Yeah.
this presentation. So the view of it not being possible is still a quandary for quite a few people, not just for the rest of.
Quite
for
a
me.
few doesn't mean everyone.
Right, but quite
Yeah.
a few, right? Still are thinking impossibility, and that it had been for a long time beforehand, trying to prove that this can be possible.
And you know, we had the same problem with the speed of sound. Your aircraft can't go faster than the speed of sound. It will blow up. It won't be, the fuselage won't be able to take the pressure. There'll be a sonic boom that'll kill the pilot. And it was like that until the 1940s.
Right?
But we got over it. And you know what? Science didn't even have to change. It just had to be applied.
Right.
So if you think about it, it is for now what some people say is implausible. But look, it is like a free force that you get from light. For you to produce light, you use so little energy, and then you can push heavy objects. So that is a propulsion. So in there. So the only thing is that to devise a way not to give up, but is still trying to devise a way to use light to move things. So one of the first solutions to use the free energy was the solar cell, but as Monroe says, you cannot pack. So you can do spacecraft, but they're gonna just go. As long as they are in a solar system, they're gonna cross planets. They can change a little bit the angle, because you can change the angle of the cell, but it cannot come back, or it cannot.
You can't slow down to go into orbit around
So,
anything.
or you can only slow down maybe if you get some insertion to planets where the solar flux is weaker than some gravitational fields. You can do a few things of that with solar. That's the first. So you use the photonic energy, and also to addition to the photonic energy, you have also the solar the solar wind that goes with particles coming out of the sun that makes the solar cells move even faster. It's not just the photons, but also the protons and neutrons and electrons that come out of the sun.
But those
And
also decay your solar sail.
yes, they make a hole eventually. So, but this is possible in one way. So why not to, say that's the impossible drive or the implausible drive. You just see that is some effect that can be used, and we are waiting for people to come, like those ideas that Monroe came and people who came before to have those ideas. But you notice something, that you can move objects with light. Now let's devise some kind of a spacecraft that can actually move stuff. That let's resolve that is a problem that needs to be solved. When we solve those problems, we come up with new technology that in 20, 30 years is in your pocket. So it's every time like that. That's an unsolvable problem. Until someone solves it, and some engineer comes, betters it, make it easy for you to apply in everything in your house or in your phone. So it's always like that. So that is one problem. We can move stuff with photons. Now let's devise something that can use that. So far, just proof of concept waiting.
Right.
And there's another
And
thing.
I have another thing.
Sure.
Midnight hour has been passed.
All right.
Just pay attention to that because we get so enthralled in everything. And there are some of us that have to get up tomorrow.
Really?
To me, go back to you to say it was goodbyes and turn off the presentation.
What?
Because Monroe put me as a presenter. That's why you can only see my face. He's turning off.
He's turning off?
Yeah, okay.
Okay, now it should go back to me, hopefully.
And
Thank you.
everybody else. Turn off the presentation too.
Okay. So thank you once again for everybody who joined and listened and offered comments. And next week is actually the International Observe the Moon night. I'm going to try to get the surveillance camera working. It may not be until later during the evening. I don't think the planets are out until around 11 o'clock. And the ones that are out, like Venus, actually goes down shortly before we start at 9. So we'd have to try later. So I'll once again explain what I've got, show off what I've got, so we can get it on record, and then we'll try and see what we can see with it. It's going to be a lot of trial and error, so just bring your patience.
It's going to be amateur hour.
Exactly.
Well, you should try it like the days before, and if some works, get some data, take some pictures or record some videos, because it could be a setup like this Saturday.
Well, that's true. I don't know what the weather is going to be like next Saturday.
It's Florida.